Hi, so we'll go ahead and try to start on time ish and let a few more people come in and we'll get started by 7:05. All right, so we're going to go ahead and get started here. My name is Kristin Lake, and let's see here. I'm going to go ahead and share my screen in just a moment. And let's see, share screen. Entire screen. There we go. All right. Okay. This can go. All right, I am not going to be able to see really the webinar while I'm doing this presentation. So any questions will be saved until the end. And then we will go ahead and address them all the way at the end. So just put them in the Q&A section. Okay. All right, so a little bit about me. I am a veterinary entrepreneur and author of the Veterinary Technician's Guide to Emergency and Critical Care book. I'm the founder of VetMed Rounds, VetMedMath, StatMath, the co-founder of VetMedology, and executive director of Animal Emergency Fund. Let's see here. Tonight, we're going to be discussing the complete guide to medical math and emergency and critical care veterinary medicine. And let's go ahead and get started here. All right, so to earn your certificate tonight, you want to go to www.vetmedology.com after the webinar. Give it about 2 hours or so for everything to be uploaded, and create an account or subscribe to VetMedology for just $10 a month if you haven't already. Navigate to the Your CE portal, and this webinar will be available to you. It says by tomorrow, but I'll be doing it late tonight. To complete the required quiz to earn your free certificate of completion by no later than Saturday, 2/17/24 at midnight. At that time, you will lose access to the course in the Your CE portal if you are not a VetMedology subscriber. VetMedology subscribers also receive free access to all live webinars. So let's go ahead and get started here. So these are the things that we're going to be discussing tonight. Percentage solutions, grams to mgs per mil, Toxaban, poison control dosage, 1 gram per kg, and resting energy requirements, both formulas, C1V1 equals C2V2, and V2 minus V1, calculating a new concentration in a syringe. Maintenance IV fluid rates, multiple methods for that. More intermediate math, dilutions with dextrose boluses, N-acetylcysteine dilution, doxycycline dilution, dividing a diluted drug between 2 syringes, stock solution dilution for dobutamine, dilutions for exotics with dexmedetomidine, calculating withdrawable blood volume and total blood volume of exotics based on weight, shock boluses, quarter and third shock dose crystalloid aliquot, KCL for any volume, and dextrose CRIs, insulin CRIs, how to calculate a CRI, midazolam CRIs in mg per kg per hour, straight and dilute, fentanyl CRI, mic per kg per hour, and mg per kg per hour, straight and dilute for a syringe pump and a fluid bag. Metoclopramide CRI in mg per kg per day. Lidocaine CRI in mics per kg per minute, straight and dilute for a syringe pump in a fluid bag. KFOS CRIs in millimoles per kg per hour. And some advanced math, calculating donor and recipient blood volumes for transfusion. Drip rates down to drops per second, calculating a blood transfusion over 4 hours with the gravity drip rate method and plum pump method. Venom vet anti-venom infusion rate titration calculation over 30 minutes and 1 hour in a dog. I believe I only did the 1 hour. I apologize. Calculating the heart rate from an ECG at 25 millimeters per second and 50 millimeters per second. H cylinder oxygen tank, PSI, remaining time. Brief overview of surgical fluid rates for canines and felines, FLK CRI for a fluid bag, changing rates, vasopressor calculation, norepinephrine, dobutamine, and dopamine CRIs, dopamine and norepinephrine vasopressor stock solution calculations, titrated cardiac CRIs, esmolol, procainamide, sodium nitroprusside, diltiazem, and with a brief review of propranolol. It's a cardiac drug, but it's not titrated. And there's a VetMedMath medical math journal and tote bag giveaway tonight. The medical math journal comes with lined and unlined pages, and the winner will also receive a tote bag and it goes to the first person who can solve the problem that I give at the end. And then there's going to be a Q&A if time permits. So just save all your questions until the end, okay? All right, what you're going to need tonight is a notebook with plenty of paper, 2 pens, pencils, and a calculator with the scientific side. If you turn your phone from the vertical to the horizontal, then you should be able to go ahead and access that. Okay, let's get started with percentage solutions, grams to mgs per mil. So this is going to be for Baytril. Concentration is 22.7%. So 1% is equivalent to 1 gram dissolved solid in 100 mils of fluid. For both drug calculations and CRIs, if your concentration is given as a percentage, work this information out first. So a 22.7% solution equals 22.7 grams per 100 mils. So 22.7 grams times 1,000 milligrams per gram gives us 22,700 milligrams, and grams cancels out. So 22,700 milligrams per 100 mils. You want to divide now, and your concentration ends up being 227 mgs per mil. So basically, we want to make sure that, we obviously are not giving Baytril straight at a 22.7% solution. We want it, ideally 1 to 10 at a 2.27% solution. So that number may change, based on your dilution. Okay. So Toxaban for poison control dosing in grams per kg. I have a video for you to watch. So we're going to be talking about Toxaban, the poison control dosing in grams per kg. Order is 1 gram per kg from poison control, and then the weight is 23.6 kgs. Our concentration of activated charcoal is 10.4%. We need to know that a 1% solution equals 1 gram of solute to 100 mils of solvent, and that 1 gram equals 1,000 milligrams. First, we're going to solve for our concentration and get it into mgs per mil. So 10.4% is equivalent to 10.4 grams per 100 mLs. We get 10,400 milligrams per 100 mLs and divide that to get 104 mgs per mil. Secondly, we need to go ahead and convert grams to milligrams. So 1 gram per kg needs to go into mgs per kg. So 1 gram per kg times 1,000 milligrams per gram gives us 1,000 mgs per kg. Now we can go ahead and calculate dose times weight divided by concentration. So 1,000 mgs per kg times 23.6 kgs gives us 23,600 milligrams. 23,600 milligrams divided by 104 mg per mil gives us 226.9 mils or 227 mils of toxaban. When it comes to rounding, wait until your final step when you have your answer to go ahead and round. Don't do incremental rounding in the problem itself. This can drastically change your answers when it comes to drugs like cardiac CRIs. So just good foundational thing there. Okay, so let's see here. All right, so just to recap that, so poison control typically suggests about 1 to 2 grams per kg, depending on the severity of the intoxication, basically. And so the weight we're working with is 6.2 kgs. Our concentration is 10.4%. We want to go ahead and work out our concentration first and convert percentage to mgs per mil. So a 1% solution again is 1 gram solute into 100 mils solvent, and 1 gram is equal to 1,000 milligrams. Concentration is 10.4%, and that gets converted to mgs per mil, and that is the math for that. So 104 mgs per mil is how that works out to be. So grams to milligrams, 1 gram per kg. We need to convert that to mgs per kg. So we go ahead and take 1 gram per kg times 1,000 milligrams per gram equals 1,000 mgs per kg. Dose times weight divided by concentration, 1,000 milligrams per kilogram times 6.2 kilograms equals 6,200 milligrams. 6,200 milligrams divided by 104 mgs per mil equals 59.6 mils toxaban. Resting energy requirement for both formulas. Let's see here. So we want a quarter of 2.5 times RER for a 1.8 kilogram kitten. And our concentration of Jevity is 1.5 kilocals per mil. You need to know your concentration. And it may be 1.2, it may be 1. You need to know that information, and it's on the bottle. So formula 1 is RER equals 70 times body weight in kgs to the 0.75 exponent. And this can be used for animals of all weights, and it's the most accurate formula. Formula 2, RER equals 30 times body weight in kgs plus 70, should not be used for animals weighing less than 2 kilograms or greater than 45 kilograms. However, you can do this with a standard calculator, and it's good to use for the VT&E. Formula 1 would be appropriate to utilize for this patient's weight. So 70 times 1.8 kilograms to the 0.75 exponent. You want to start with your parentheses and use the x to the y function on the scientific side of your calculator app. So 1.8 to the 0.75 equals 1.55. And 1.55 times 70 equals 108 kilocals per day, and that's the RER. So 2.5 times RER is what we need to figure out now. So 2.5 times 108.78 kilocals per day equals 271.95 kilocals per day. Now, a quarter of 2.5 times RER is what we need to figure out. So 271.95 kilocals per day divided by 4 equals 67.98 kilocals per day. You want to now divide by the concentration, then find the rate and the volume. So 67.98 kilocals per day divided by 1.5 kilocals per mil gives you 45.33 mils per day divided by 24 hours per day equals 1.88 mils per hour, which is your rate. And then you want to multiply by time, which is 6 hours is a good amount of time to go ahead and pull up Jevity or any other nutritional support solution for, as it won't go rancid. And 11.33 mils is our total volume. Let's see here. Okay, so Formula 2 would not be appropriate to utilize for this patient's weight, and we're going to show why. So RER equals 30 times body weight in kgs plus 70 for this formula. So 30 times 1.8 kgs plus 70. You want to start with the multiplication. So 30 times 1.8 gives us 54. 54 plus 70 gives us 124 kilocalories per day for the RER versus 108.78 kilocalories per day. Every meal counts in small and underweight patients. They can easily be fluid overloaded, especially if receiving enteral nutrition, free water flushes, and IV fluid therapy. They may also be at risk for refeeding syndrome and may be at risk for fluid electrolyte imbalance. 2.5 times RER for this amount. So 2.5 times 124 kilocalories per day equals 310 kilocalories per day versus 271.95 kilocalories per day. And a quarter of 2.5 times RER. 310 kilocalories per day divided by 4 is 77.5 kilocalories per day versus 67.98 kilocalories per day. Again, divide by the concentration, then find the rate and volume. 77.5 kilocalories per day divided by 1.5 kilocalories per mil equals 51.67 mils per day divided by 24 hours per day equals 2.15 mils per hour for the rate times the time of 6 hours equals 12.92 mils total volume. So calculating a new concentration in a diluted syringe using C1V1 equals C2V2 and V2 minus V1. Our order is 1 ml of dopamine diluted. The total volume in the syringe is 35 mils. The concentration of dopamine is 40 mg per ml. So C1V1 equals C2V2. You want to plug in your values according to the chart and solve for C2. So this is basically a rundown of what each variable stands for. So C1 is the concentration of the medication in mics per mil, mgs per mil, MEQs per mil, percentages, etc. V1 is the volume of medication in mils. C2 is the final concentration in mics per mil, mgs per mil, MEQs per mil, percentage, etc. And V2 is your final volume in mils. V2 minus V1 is going to give you the volume of diluent that you need if you haven't added it yet. So let's see here. So first we want to go ahead and plug in our numbers. 40 mgs per mil times 1 mil equals C2 times 35 mils. Multiply and cancel. So 40 milligrams equals C2 times 35 mils. And then divide both sides by 35 mils. So 40 milligrams divided by 35 mils equals C2 times the 35 mils that gets canceled out. Let's see here. So 1.14 mgs per mil equals C2, which is our new concentration. So V2 minus V1 is going to give us the volume of diluent. So 35 mils minus 1 mil. We want to go ahead and take the final volume minus the volume of medication, and that's going to give us how much diluent is in that syringe. All right, so maintenance IV fluid rates, there's multiple methods here. So calculating maintenance IV fluid rate, the order 1 times maintenance is the 1xm, and that equals 60 mils per kg per day. Weight is a 12 kilogram canine, and time is 24 hours, which is 1 day. So to calculate maintenance IV fluid rates, these are the different maintenance rates, basically. For a canine, you'll see that they're based off of 60 mils per kg per day. And for a feline, you'll see that they're based off of 40 mils per kg per day. So to go ahead and calculate this, we take 60 mils per kg per day times 12 kgs equals 60 mils per day. Equals 720 mils per day. 720 mils per day divided by 24 hours per day gives us 30 mils an hour. Now, to calculate maintenance IV fluid rate with the dehydration deficit and ongoing losses factored in. So same order, basically, 1 times maintenance at 60 mils per kg per day. Weight is 12 kilogram canine. The dehydration deficit is about 5%, and time is 24 hours, 1 day. So this is basically a chart here that allows you to see how you can determine what the dehydration deficit is according to physical examination findings. For the first 24 hours of hospitalization, you want to correct 80% of the dehydration deficit. If calculating fluids over 12 hours, do not calculate the 80% correction of the dehydration deficit. Ongoing losses are fluid losses from vomiting and or diarrhea, not necessary to factor in for patients that are not vomiting or do not have diarrhea in most circumstances. And 1 mil per kg per hour is our best estimation of sensible and insensible losses. So at the end, we're going to add together the maintenance IV fluid rate, the dehydration deficit rate, and ongoing losses rate for the total IV fluid rate. So let's see here. All right, so for our maintenance fluid rate, again, the 60 mils per kg per day for a 12 kg canine gives us 30 mils an hour. So calculating the dehydration deficit with 80% correction over 24 hours, we need to go ahead and convert that about 5% into a decimal and that 80% into a decimal as well. We're going to take 12 kilograms and multiply by 0.05 liters per kg. And that will give us 0.6 liters. So 0.6 liters times 1,000 mils per liter is going to give us 600 mils. So 600 mils times 0.8, which is the 80% correction, is 480 mils. So 480 mils divided by 24 hours equals 20 mils an hour. So estimated ongoing losses are 1 mil per kg per hour. So we just multiply the 1 mil per kg per hour times 12 kilograms, and that equals 12 mils an hour. And then we add all of the rates together. So 30 mils an hour plus 20 mils an hour plus 12 mils an hour gives us 62 mils an hour for our total IV fluid rate with dehydration deficit and ongoing losses factored in. So this is another way to go ahead and calculate maintenance IV fluid rate that's used in practice. I'll let you take a look at this. So this fluid rate equation is similar to the rate in the literature stated that I stated previously, but is good for calculating maintenance fluid rate on dogs, cats, kittens, and puppies that is more comparable to their actual weights, but does not account for dehydration deficit or ongoing losses. The previously stated process for accounting for these is well documented and superior, but this method is used in practice. All right. This is how SmartFlow actually calculates maintenance fluid rates, which is a little interesting. I hadn't seen this prior to finding it in the program one day, but that's how it compares to the 60 mil per kg per day equation. It's a little bit higher. All right, this is the AHA maintenance fluid rate equation that's used in practice. So a lot of practices utilize this. So for a 3.3 kilogram cat, basically 8.16 mils an hour. We were getting about 8.2 anyways with the other one. So it's pretty on par. All right, so dilutions for dextrose boluses. Our order is 0.5 mils per kg. The weight is a 3 kilogram feline. The concentration is 50% dextrose diluted. Dilution ratios, 1 to 1 equals 2 total parts. It's half drug, half diluent. 1 to 4 is 5 total parts. And 1 to 10 is 11 total parts. Anything over 7.5% dextrose is a vesicant if it extravasates. I have seen these extravasations and they are very gnarly. You do not want this to happen to your patient. So you want to make sure that you are flushing that catheter before you inject dextrose into any IV. So for 1-to-1 dextrose, that turns it into 25% dextrose, which is a vesicant. But in a stat situation, we will utilize 25% dextrose. 1-to-4 is 10% dextrose, and it's a little bit better to go ahead and do any kind of repeat boluses once the immediate emergency is taken care of, basically with at least a 1-to-4 to 1-to-10 dilution that is given slowly. A 1-to-10 dilution is equivalent to 4.5% dextrose. So for 1-to-1, 25% dextrose, you want to go ahead and take 0.5 mils per kg, our order times our weight of 3 kgs, and that gives you 1.5 mils of dextrose, which is one part, and then you're going to add 1.5 mils of diluent for another part. All right. For 1-to-4, 10% dextrose, 0.5 mils per kg times 3 kgs equals 1.5 mils dextrose, which is one part. 1.5 mils times 4 equals 6 mils diluent, which is 4 parts. Add them together. 1.5 mils plus 6 mils equals 7.5 mils total volume, which is 5 parts. 1-to-10, 4.5% dextrose, 0.5 mils per kg times 3 kgs equals 1.5 mils dextrose, 1 part. 1.5 mils times 10 equals 15 mils diluent, 10 parts. 1.5 mils plus 15 mils equals 16.5 mils total volume, which is 11 parts. All right, now we're going to talk about N-acetylcysteine, 20%, the loading dose and additional dose dilution. This is the dosing for acetaminophen toxicity. So the order is 140 mg per kg loading dose once, then 70 mg per kg dosage every 6 hours for 7 treatments. The weight we're working with is 30 kgs. The rate, we don't know, so we put a variable there. The fluids, we don't know, so we put a variable there. The time is 20 minutes, so you want to give it IV slow on a syringe pump. Concentration is 20%, which ends up being 200 mg per mil, but we need to dilute it to 5%, which is 50 mg per mil, by diluting 1-to-3 with 0.45% NaCl, which is half strength saline, sterile water, or D5W. You want to use a 0.2 micron filter at the port closest to the patient. You also want to draw it up with a filter needle. So the dilution ratio, have over want. You want to take 20% and divide it by 5%, and that gives you 4 total parts. So 1-to-3 is how you figure out your dilution. Loading dosage, 140 mg per kg times 30 kgs equals 4,200 milligrams. 4,200 milligrams divided by 200 mg per mil equals 21 mils NaC. And loading dosage, dilution, and rate. So 21 mils NaC, 1-to-3 in either half strength saline, sterile water, or D5W. Remember that 1-to-3 is 4 total parts. So 21 mils times 4 equals 84 mils, and that's our total volume of 4 parts. Minus 21 mils NaC, which is 1 part, gives us 63 mils of our diluent, which is 3 parts. Now to figure out our rate, you take 60 minutes divided by 20 minutes, which is 3, which is a unit of time. So 84 mils total volume times 3. It gives you a rate of 252 mils an hour to deliver it over. All right. So for the additional doses, dilution, and the rate, so additional doses are half of the loading dose at 70 mg per kg times 30 kgs equals 2,100 milligrams. 2,100 milligrams divided by 200 mg per mil equals 10.5 mils NaC. Remember, 1-to-3 is 4 total parts, and 10.5 mils times 4 equals 42 mils total volume, which is 4 parts, minus 10.5 mils NaC, which is 1 part, gives us 31.5 mils diluent, which is 3 parts. Again, 60 minutes divided by 20 minutes equals 3, which is a unit of time. So 42 mils times 3 equals 126 mils an hour for our rate. All right, to check your dilution math for your loading dose, 4,200 milligrams divided by 50 mg per mil equals 84 mils. So a total volume of 84 mils is required to get a 5% 50 mg per mil dilution. Additional doses, 2,100 milligrams divided by 50 mg per mil equals 42 mils. So a total volume of 42 mils is required to get a 5% 50 mg per mil dilution. Of note, N-acetylcysteine contains sodium, and to prevent excess sodium, hypernatremia, and fluid creep over the course of hospitalization, it is recommended not to dilute N-acetylcysteine with 0.9% NaCl, but rather the half-strength saline, sterile water, or D5W. You want to place a filter needle on your syringe and draw up the drug. Attach a 0.22 micron filter to the end of the extension set and attach the filter at the port closest to the patient. Use a dedicated extension set and change the filter after every 50 mils of diluted NaC delivered. So for doxycycline, 100 mg per mil, dilution to 1 mg per mil. We want to dilute 1 to 10. And that the order is 5 mg per kg IV BID. And the weight that we're working with is 40.6 kgs. Rate is unknown. Time is 1 hour. Concentration is 100 mg per mil. You want to reconstitute with 10 mils of 0.9% NaCl, which gives you a 10 mg per mil solution. And then you want to dilute. I'm sorry, it says 2 different dilutions here. I need to fix that. But I believe it's 1 to 10, not 1 to 9. So yes. So basically, you want to go ahead and dilute 1 to 10 to a 1 mg per mil dilution. So 5 mg per kg times 40.6 kgs equals 203 milligrams. 203 milligrams divided by 10 mgs per mil equals 20.3 mils doxy. 20.3 mils times 10 equals 203 mils total volume, which is 10 parts. Minus 20.3 mils of doxy, which is 1 part, gives you 182.7 mils diluent, which is 9 parts. Your diluent choice should be a 250 mil IV fluid bag of saline. So 203 mils times 1 hour gives you 203 mils an hour. If you wanted to go ahead and extend it, that would be a little bit different, but generally 1 hour is what it goes over. Use a 250 mil bag of 0.9% NaCl and remove 47 mils of saline first. So 203 mils minus 182.7 mils gives you 20.3 mils, which is the amount of doxycycline that we calculated. So add 20.3 mils of the 10 mg per mil doxycycline to 182.7 mils diluent. And then you will have a 1 mg per mil solution. Ask your DVM if they would like to stop IV fluid therapy during the infusion, because it's preferable so as to not fluid overload the patient, as doxycycline can be great volumes, especially for larger dogs. The infusion itself can be extended to 2 hours. Dividing a diluted drug between 2 syringes. So doxycycline again, 5 mg per kg IV BID. The weight is 18 kgs. The rate is unknown. Time 1 hour. And we are going to, it says 1 to 9 again, it's 1 to 10. Let me see here. Yeah. So 5 mgs per kg times 18 kgs is 90 milligrams. 90 milligrams divided by 10 mgs per mil equals 9 mils doxy. 9 mils doxy times 10 equals 90 mils total volume minus 9 mils doxy equals 81 mils diluent. 90 mils divided by 2 syringes equals 45 mils per syringe. So 9 mils doxy divided by 2 syringes equals 4.5 mils doxy per syringe. 81 mils diluent divided by 2 syringes equals 40.5 mils diluent per syringe. The rate of 45 mils per syringe times 2 syringes over an hour gives us 90 mils an hour. Oops. Hang on. There we go. The infusion is over 1 hour. So we would need to set each syringe to infuse over 30 minutes. So each 45 ml syringe would go on a syringe pump at 90 mils an hour. Okay, so stock solution dilutions. The order is 1.5 mils dilute dobutamine, which is 12.5 mgs per mil. The total volume is 60 mils, 0.9% NaCl. The rate, we're going to start at 1 mil per kg per hour, which is equivalent to 5 mics per kg per minute. And you can increase it up to 4 mils per kg per hour IV for a canine. The weight is 20 kilograms. The concentration of this stock solution is 0.3 mgs per mil or 300 mics per mil. So how do we calculate a stock solution? Dobutamine, 12.5 mg per mil stock solution. Basically, the 1.5 mils, we want to go ahead and multiply by the concentration to find our milligrams that are in that 1.5 mils. So 1.5 mils times 12.5 mg per mil equals 18.75 milligrams. And then 18.75 milligrams divided by 60 mils gives us 0.3125 mg per mil or 0.3 mg per mil. Calculate a dobutamine CRI for the starting rate for 1 hour with your stock solution concentration. So our order is 5 mics per kg per minute. The weight is 20 kgs, time is 1 hour, concentration is 0.3 mgs per mil. 5 mics per kg per minute times 20 kgs equals 100 mics per minute. 100 mics per minute times 60 minutes an hour equals 6,000 mics an hour. 6,000 mics an hour times 1 hour equals 6,000 mics. 6,000 mics divided by 1,000 mics per mg equals 6 milligrams. 6 milligrams divided by 0.3 mg per mil equals 20 mils dobutamine at the 0.3 mg per mil concentration. And the rate is 20 mils divided by 1 hour equals 20 mils per hour. The feline dosage is 2.5 to 15 mics per kg per minute, which is equal to 0.5 to 3 mils per kg per hour. Start at the 0.5 mil per kg per hour and increase up to 3 mils per kg per hour with 1.5 mils dobutamine to 60 mils, 0.9% saline. Again, it equals 300 mics per mil or 0.3 mgs per mil. If you use the body weight mode on a syringe pump, it may not allow it because the volume is just greater than 60 mils in the syringe, and it will throw off the concentration basically and the rate. So you just want to go ahead and set the pump for the rate mode. So let's see here. Okay. All right. So to go ahead and calculate for 1 mil per kg per hour, which is equivalent to 5 mics per kg per minute, we just basically do 1 mil per kg per hour times the weight, and we get 20 mils an hour. We get our rate. It's particularly useful to utilize stock solutions in emergency surgery and stat situations as it requires minimal math, and the math that is required can be done on a calculator app, and dosing ranges, volumes can be easily memorized for specific drugs and administered with maximum efficiency. So for 2 mils per kg per hour, we're just doubling things. And that's equivalent to 10 mics per kg per minute. So 2 mils per kg per hour times 20 kgs equals 40 mils an hour. And then we double again, 4 mils per kg per hour, which is the max that we want to use in a canine, equals 20 mics per kg per minute. So 4 mils per kg per hour times 20 kgs equals 80 mils an hour. Let's see here. Okay, so this is the dexmedetomidine dilution for exotics. We're going to be talking about dexmedetomidine dilution for exotics. The order is 0.065 mg per kg IM. The weight is a 35-gram reptile, and the concentration of dexmedetomidine is 0.5 mg per mil. First thing we need to do is convert from grams to kilograms. So 35 grams divided by 1,000 grams per kilogram equals 0.035 kilograms. Next, we need to go ahead and take our dosage, 0.065 mg per kg times 0.035 kilograms, cancel out kilograms, and get 0.002275 milligrams. 0.002275 milligrams divided by the original concentration of 0.5 mg per mil gives us 0.00455 mils, which is not a withdrawable volume, so we must dilute. So a good jumping off point is to go ahead and start with 1/10 of the original concentration. So that's where we get 0.05 from. So first we take 0.5 mg per mil, divide by 0.05 mg per mil. Mg per mil cancels out, and we get 10 total parts, which is a 1:9 dilution. So another good jumping off point is to start with either 0.01 mils, 0.1 mils, or 1 mil of neat full strength drug. So we're going to start with 0.01 mils of 0.5 mg per mil dexmedetomidine, multiply that by 9, and we get 0.09 mils diluent, which is equivalent to a 0.05 mg per mil dilution. 0.01 mils is 1 part, 0.09 mils is 9 parts. So then we go ahead and take our original milligrams and divide by our concentration. So 0.002275 milligrams divided by 0.05 mg per mil equals 0.0455 mils, or 0.05 mils, which is also 5 units on a U100 syringe. On a U100 syringe, every 0.01 mils is equivalent to 1 unit. Okay. All right. So our order, 0.015 mg per kg IP for a 40-gram mouse. Our concentration is 0.5 mg per mil of dexmedetomidine. We need to know that 1,000 grams equals 1 kilogram. So 1,000 grams per kg, and that 0.01 mils equals 1 unit on a U100 syringe. First, we want to work out grams to kilograms. 40 grams divided by 1,000 grams per kg gives us 0.04 kgs. Dose times weight divided by concentration, 0.015 mg per kg times 0.04 kgs equals 0.0006 milligrams. 0.0006 milligrams divided by 0.5 mg per mil gives us 0.0012 mils dexmedetomidine, which is not a withdrawable volume, so we must dilute. The dilution, we want to go ahead and do a 1:9 dilution, which is 10 total parts. And 0.5 mg per mil divided by 0.05 mg per mil gives us that 10. A good jumping off point is to start with either 0.1 mils, 0.01 mils, 0.1 mils, or 1 mil of neat full strength drug. For dexmedetomidine, 0.5 mg per mil, 0.01 mils, or 0.1 mils would be most appropriate. So 0.05 mg per mil dilution of Dexmed. Let's see here. So 0.01 mils of 0.5 mg per mil Dexmed times 9 is going to give us 0.09 mils diluent. And the 0.01 mils is 1 part, and the 0.09 mils is 9 parts. So 10 total parts. Let's see here. Add those together and you get 1 mil total volume of diluted Dexmed, and 0.006 milligrams divided by 0.05 mg per mil, the new concentration, equals 0.012 mils, which is 1.2 units on a U100 syringe of the 0.05 mg per mil diluted stock solution. So you want to remove 1.2 units. You can eyeball this between 1 and 2 units from 1 mil of diluted Dexmed, from 1 mil of a diluted Dexmed syringe, and deliver it to the patient. Next is withdrawable blood volumes from exotics. We're going to be talking about withdrawable blood volume from exotics. So basically, total blood volume in exotics is about 6 to 8% of their body weight in grams. We do start to see physiological responses when 10% of their total blood volume is removed. So we want to stay in that 6 to 8% range at all times. There's two methods for how much is safe to draw, either 1% of the body weight in grams or 1 ml per 100 grams of body weight. We need to know that 1 ml of blood is equivalent to 1.06 grams. So 1.06 grams per mil is part of this calculation. For an 860 gram rabbit, we calculate our total blood volume at 8% of 860 grams. So 860 grams times 0.08, which is equivalent to 8%, gives us 68.8 grams. We divide that by the 1.06 grams per mil of blood, and we get 64.9 mils for the total blood volume. The first method is the safe to draw method of 1% of body weight in grams. And so 860 grams times 0.01, which is 1%, equals 8.6 grams. Divided by 1.06 grams per mil of blood, we get 8.1 mils of blood with that method. With the second method, the 1 mil per 100 grams of body weight, we take 860 grams divided by 100 grams per mil, and we get 8.6 mils of blood. So somewhere between 8.1 and 8.6 mils of blood is likely safe to take. Again, at 10% of total blood volume removed, we can start to see physiological responses, and we start to see this a lot more readily in the smaller patients, basically, that we need the blood, but it's difficult to go ahead and obtain it. So use those microhematocrit tubes, definitely. For a 100 gram hamster, we calculate the total blood volume of 8% of 100 grams. 100 grams times 0.08, which is 8%, equals 8 grams, divided by 1.06 grams per mil of blood, equals 7.5 mils total blood volume. So the first method, 1% of body weight in grams, equals 100 grams times 0.01 or 1% equals 1 gram, divided by 1.06 grams per mil of blood equals 0.94 mils of blood. And the second method of the 1 mil per 100 grams of body weight, well, we've got 100 grams of body weight, so it's 1 mil of blood. All right, so for a 980 gram rabbit, our total blood volume is 8%. Total blood volume is between 6 and 8% of the body weight in grams. Safe to draw method is 1% of the body weight in grams, or 1 mil per 100 grams of body weight, so 100 grams per mil. We need to know for the safe to draw method that 1.06 grams equals 1 mil of blood, so 1.06 grams per mil. For a 980 gram rabbit, total blood volume equals 8% of 980 grams. So 980 grams times 0.08 equals 78.4 grams. 78.4 grams divided by 1.06 grams per mil equals 73.96 mils total blood volume. Safe to draw, 1% of body weight in grams method. 980 times 0.01 equals 9.8 grams. 9.8 grams divided by 1.06 grams per mil equals 9.25 mils of blood. The 1 mil per 100 grams of body weight method, 980 grams divided by 100 grams per mil equals 9.8 mils of blood. Okay, calculating quarter and third shock dose crystalloid aliquots. Okay. So for canines, 60 to 90 mils per kg is the total shock dose for our dogs. The lower end is utilized in cardiac or renal impairment. For felines, it's 40 to 60 mils per kg for total shock dose, and lower end also used in cardiac and renal impairment. Always give in 1/3 to quarter shock dose aliquots. It's called a fluid challenge. You never want to give a total shock dose unless the animal is bleeding out faster than what you're able to get fluids in. And at that point, you should just be slamming fluids in with a slam bag. So option one is by hand with the fraction, 90 mils per kg shock dose for a dog, then quarter shock dose aliquot. We need to figure that out. Weight is 15 kilograms, and the time that it's going to be given over is 15 minutes. So 90 mils per kg times 15 kilograms equals 1350 mils, which is our total shock dose. So 90 mils per kg times 1/4 equals 90 over 1 mils per kg times 1/4, which gives us 90 divided by 4 and 22.5 mils per kg. 22.5 mils per kg times 15 kilograms equals 337.5 mils, which is our quarter shock dose aliquot, and our VTBI when we set our pump. 60 minutes divided by 15 minutes equals 4. 4 is a unit of time. So 337.5 mils times 4 equals 1350 mils an hour, which is our rate over 15 minutes. So our rate's 1350 mils an hour. Our VTBI is 337.5 mils. Option two, this is with the calculator and with decimals. It's going to be 90 mils per kg shock dose, then a quarter shock dose aliquot. Weight again is 15 minutes and time again is 15 minutes. So 90 mils per kg times 15 kgs equals 1350. Total shock dose, 1350 times 0.25, which is 1/4 in decimal form, equals 337.5 mils, which is our quarter shock dose aliquot and VTBI. 60 minutes divided by 15 minutes equals 4. 4 is a unit of time. 337.5 mils times 4 gives us 1350 mils an hour for our rate over 15 minutes. So the exact same thing. This is how to calculate the third shock dose aliquot by hand with a fraction for, again, a 15 kg dog and over 15 minutes. 90 mils per kg times 15 kgs, 1350 for the total shock dose. 90 mils per kg times 1/3 equals 90 over 1 mils per kg times 1/3 equals 90 divided by 90 over 3 equals 30 mils per kg. So 30 mils per kg times 15 kgs equals 450 mils. This is our third shock dose aliquot. And VTBI, 60 minutes divided by 15 minutes equals 4. 4 is a unit of time. 450 mils times 4 equals 1800 mils an hour, which is our rate over 15 minutes. And with a calculator with a decimal, 1/3 is equivalent to 0.333 on a calculator. The more threes you have, the more accurate it's going to be. 90 mils per kg is the shock dose again, 15 kgs over 15 minutes. So 90 mils per kg times 15 kilograms equals the 1350 mil total shock dose. And then 90 mils per kg divided by 3 equals 30 mils per kg. 30 mils per kg times 15 kilograms equals 450 mils, which is our third shock dose aliquot in our VTBI. 60 minutes divided by 15 minutes equals 4. 4 is a unit of time. 450 mils times 4 equals 1800 mils an hour. And that's our rate in VTBI. To bolus on a fluid pump, you always set your VTBI to your shock dose aliquot volume and your rate to 10 to 30 minutes for crystalloids by multiplying your shock dose aliquot by 6 for 10 minutes, 4 for 15 minutes, 3 for 20 minutes, or 2 for 30 minutes. And set that number as your rate. We're going to work on calculating KCL for any volume now. So the order of KCL is 30 MEQs per liter. We're using a Buretrol, and there's 78 mils left in it of plain fluid. And our concentration of KCL is 2 MEQs per mil. We need to know that 0.1 liters equals 10% of 1 liter and 100 mils. So we're going to calculate KCl for 78 mils. So 30 MEQs per liter divided by 2 MEQs per mil equals 15 mils per liter of KCl. 78 mils divided by 1,000 mils per liter equals 0.078 liters. So 15 mils per liter times 0.078 liters cancels out, gives us 1.17 mils KCl for 78 mils of IV fluid. Calculating a dextrose CRI. The order is 5% dextrose. The fluid is a 100 mil butyral, and the concentration of dextrose is 50%. So to calculate 5% dextrose for 100 mils, we want to take 100 times 5. Yes, it's a percent. It's represented there, but you really don't need to put it. So 100 times 5 equals 500. 500 divided by 50, again, you don't need to represent the percentage if you don't want to, equals 10 mils of 50% dextrose to 100 mils IV fluid. Calculating an insulin CRI. So for Humulin R, we basically need to know how to go ahead and do this, especially for our DKA patients. So the weight is going to be a 5.1 kilogram cat. 250 mil bag of saline is what is always used. And concentration of Humulin R is 100 international units per mil. Remember to refer insulin CRIs to bleed the line 50 mils once the insulin is already in the bag, because that insulin needs to go ahead and coat that PVC so that it does not adhere to the plastic because it binds to plastic. So the cat dosage is typically 1.1 units per kg of Humulin R. It can be 2.2. It depends on the doctor. The dog dosage, though, is 2.2 units per kg Humulin R. So for the cat dosage for Humulin R, we're going to take 1.1 units per kg times 5.1 kilograms. That gives us 5.61 units of Humulin R. And we're going to put 5.61 units into a 250 mil bag of 0.9% NaCl. You really don't need to remove anything from the bag first because it's practically a negligible amount. So this is a chart basically from my book, The Veterinary Technician's Guide to Emergency and Critical Care, about insulin CRIs, reminding you of all of these things, as well as the BG ranges and the insulin CRI rates, and when to institute different dextrose concentrations. All right, so this is how to calculate a CRI, basically. So a CRI is utilized when a patient requires a drug that is steadily dosed in a given rate over time. It is too labor intensive to have a veterinary technician slowly push all drugs, and sometimes a drug needs to be administered in an equivalent portion through a patient's therapy. This is usually achieved by using a syringe pump or a fluid pump. There are many different CRI calculations for the different drugs that can be utilized for infusion therapy. The following is a collection of CRIs with the math included, since we do not routinely use computer calculators in the veterinary field as they do in human medicine. We still work the math in most cases. It's a good experience to know this kind of math, as it will help you with other drug calculations as well. The first thing you need to do when approaching a CRI is to write down your order, weight, rate, fluids, time, and concentration. This will allow you to have all the necessary information to complete the algebraic formulas that follow. One of the simplest CRIs is for midazolam, which we'll be doing first. It's good practice to write whether a drug is light sensitive, precipitates, or binds to plastic, like insulin CRIs, on your CRI label, so that you can remember to take steps to protect the medication or to bleed your line. Light sensitive and indicates that ultraviolet light can cause photodegradation to sensitive medications in a solution through oxidation, hydrolysis, and loss of potency. Precipitation means that crystallization can occur and binds to plastic. It can occur and binds to plastic means that a medication can adhere to plastic or PVC. So we bleed the line to ensure the plastic is thoroughly coated prior to running the medication. So a CRI would be set up to like this. Basically, at the beginning, you would want to go ahead and state whether it's light sensitive, if it precipitates, or if it binds to plastic. You want to indicate whether your CRI is straight or dilute. A CRI that's straight is just the drug straight with no other fluid to dilute it in. A diluted CRI is the drug diluted in a volume of fluid and gives you a new concentration. The order is your doctor's order. So mics per kg per minute, mgs per kg per hour, whatever, dosage they want to go ahead and prescribe. The weight is your patient's weight in kilograms. The rate is how you will deliver your drug over time, either mils per hour, mils per kg per hour, mils per kg per day. If unknown, place a variable here. Fluids, this is if your drug is diluted or added to a fluid bag. It is the amount of fluid your drug is diluted in, either mils or liters. If unknown, place a variable here. Time is the time frame the drug needs to last, either in minutes or hours. If unknown, place a variable here. Concentration is your drug's concentration. All right, so we're going to calculate a midazolam straight CRI first in mg per kg per hour. So we indicate at the top that it's light sensitive, and our order is 0.2 mg per kg per hour. Our weight is 30.3 kilograms. Our rate is not known yet. Our time is 10 hours, and our concentration of midazolam is 5 mg per mil. So we start out with order times weight, which is going to give us milligrams per hour. So 0.2 mg per kg per hour times 30.3 kgs equals 6.06 milligrams an hour. 6.06 milligrams an hour times 10 hours equals 60.6 milligrams midazolam. So let's see here. Then we want to go ahead and take milligrams divided by our concentration to give us our mils in our total volume. So 60.6 milligrams divided by 5 mg per mil equals 12.12 mils midazolam total volume. So 12.12 mils midazolam divided by 10 hours gives us a rate of 1.212 mils an hour. And we always figure out basically our rate by taking the total volume in mils and dividing by time. Let's see here. So to set your syringe pump, you want to choose the mil per hour or rate option and enter 1.2 mils per hour as the rate in 12 mil syringe size. And your pump is now set for a 10-hour infusion of midazolam. All right, so this is how to calculate a dilute midazolam CRI mg per kg per hour. So it's pretty much the same order, 0.2 mg per kg per hour for 30.3 kgs. We're going to run it at 2 mils an hour. That's going to be our dilution. And our fluids are unknown. The time is over 10 hours, and our concentration of midazolam is 5 mg per mil. Calculate your CRI first. 0.2 mg per kg per hour times 30.3 kgs equals 6.06 milligrams per hour. Again, order times weight is going to give you milligrams per hour. And then milligrams per hour times time is going to give you milligrams. So 6.06 milligrams per hour times 10 hours equals 60.6 milligrams. 60.6 milligrams divided by 5 mg per mil. Our milligrams divided by our concentration is going to give us our mils and our volume of drug. So 12.12 mils of midazolam. Dilution. 2 mils an hour times 10 hours, it gives us 20 mils total volume. So our rate times our time equals our mils in total volume. So total volume minus volume of drug is going to give us our diluent. So 20 mils minus 12.12 mils, it gives us 7.88 mils of 0.9% NaCl to use as diluent. Calculating a fentanyl straight CRI in mics per kg per hour and mgs per kg per hour on a syringe pump. So we want to indicate that it's light sensitive initially. And then our order of fentanyl is 3 mics per kg per hour. Weight is 3.6 kilograms. Rate is not known. Time is 12 hours. And our concentration of fentanyl is 50 mics per mil. So to calculate it in mics per kg per hour, 3 mics per kg per hour times 3.6 kgs equals 10.8 mics an hour. 10.8 mics an hour times 12 hours equals 129.6 mics. 129.6 mics divided by 50 mics per mil equals 2.592 mils fentanyl. 2.592 mils divided by 12 hours gives us a rate of 0.216 mils an hour. And if you need to convert micrograms to milligrams, that's shown. I typically would not run any CRI under 1 mil an hour. So if I got a straight fentanyl CRI that said 0.216 mils an hour, I would go ahead and do the diluted CRI math at that point. Milligrams per kg per hour. So this is equivalent to 0.003 milligrams per kg per hour. And let's see, 3.6 times 3.6 kilograms equals 0.018 milligrams an hour. 0.018 milligrams an hour times 12 hours equals 0.1296 milligrams. And 0.1296 milligrams divided by 0.05 mgs per mil, because 50 mics per mil turns into 0.05 mgs per mil, equals 2.592 mils fentanyl. 2.592 mils fentanyl divided by 12 hours. Again, we get the same rate, 0.216 mils an hour. Okay, so this is a dilute fentanyl CRI in mics per kg per hour on a syringe pump. Again, we say that it's light sensitive. Order is 4 mics per kg per hour. The weight is 6 kilograms. We're going to run it at 4 mils an hour because that's sensible to do, make it match basically, so that it's easy to go ahead and titrate up and down. Fluid is not known, and the time is 12 hours. Concentration of fentanyl, again, is 50 mics per mil. So you just calculate your CRI. 4 mics per kg per hour times 6 kgs equals 24 mics an hour. 24 mics an hour times 12 hours equals 288 mics. 288 mics divided by 50 mics per mil equals 5.76 mils fentanyl. The dilution, 4 mils an hour times 12 hours is 48 mils total volume. 48 mils minus 5.76 mils equals 42.24 mils diluent, basically. So you're going to draw up 5.76 mils of fentanyl in a syringe and then draw up 42.24 mils of diluent in a syringe. Add the syringes together to equal 48 mils. Set your syringe pump rate to 4 mils an hour and your VTBI to 48 mils. And your time should be 12 hours as a check. All right, so how to calculate dilute fentanyl CRI mics per kg per hour in a 1 liter fluid bag. Again, we say that it's light sensitive at the beginning. Order is 5 mics per kg per hour. Weight is 20 kgs. The rate is going to be 5 mils per kg per hour. And we don't know what that quite is yet. Our fluid is 1 liter, which is 1,000 mils. Time is unknown at this point in time. And concentration is 50 mics per mil. First, we want to calculate our rate and our fluid bag time first. So 5 mils per kg per hour times 20 kgs equals 100 mils an hour. Now we take the volume of the bag, which is 1,000 mils, and divide it by the rate, 100 mils an hour, and that gives us 10 hours as our fluid bag time. So now we've just solved basically our variables. Now we can go ahead and calculate our fentanyl CRI and plug in this information. So 5 mics per kg per hour times 20 kgs equals 100 mics an hour. 100 mics an hour times 10 hours equals 1,000 mics. 1,000 mics divided by 50 mics per mil equals 20 mils fentanyl. So you'll want to remove 20 mils of fluid from your fluid bag, add 20 mils of fentanyl to your fluid bag, mix it well. Set your IV pump to 100 mils an hour and your VTBI to, let's see here, your VTBI should be the either 999 mils or 1000 mils, depending on the pump that you're using. And your time will either be 9.99 or 10 hours as a check. So for metoclopramide CRIs, mgs per kg per day in 1 liter fluid bag, we want to indicate that it's also light sensitive. The order is 2 mgs per kg per day, and the weight is 18 kilograms. The rate is going to be run at 1 times maintenance at 60 mils per kg per day. Fluid is 1 liter of plasmolite. Time is unknown. Concentration is 5 mg per mil of metoclopramide. We want to calculate the maintenance fluid rate and the fluid bag time first. So 60 mils per kg per day times 18 kgs equals 1,080 mils per day. 1,080 mils per day divided by 24 hours per day equals 45 mils an hour for our rate. 1 liter equals 1,000 mils. So 1,000 mils divided by 45 mils an hour equals 22.2 hours. Now we need to plug in that information to our CRI. 2 mgs per kg per day times 18 kgs equals 36 milligrams per day. 36 milligrams per day equals 24 hours per divided by 24 hours per day equals 1.5 milligrams per hour. 1.5 milligrams per hour times 22.2 hours, our fluid bag time, equals 33.3 milligrams. 33.3 milligrams divided by 5 mg per mil equals 6.66 mils metoclopramide to 1 liter plasmolite. All right, so calculating a lidocaine straight CRI in mics per kg per minute on a syringe pump. Let's see here. Again, light sensitive. Our order is 50 mics per kg per minute. The weight is 38 kgs. We don't know the rate yet. The time is going to be 10 hours, and the concentration of lidocaine is 2% or 20 mgs per mil. So we're going to calculate our CRI. 50 mics per kg per minute times 38 kgs equals 1,900 mics per minute. 1,900 mics per minute times 60 minutes per hour equals 114,000 mics an hour. 114,000 mics an hour divided by 1,000 mics per milligram equals 114 milligrams per hour. 114 milligrams per hour times 10 hours equals 1,140 milligrams. 1,140 milligrams, let me see here. That should just say milligrams. Divided by 20 mgs per mil equals 57 mils lidocaine total volume. Calculate your rate. Total volume divided by time equals rate. So 57 mils lidocaine divided by 10 hours equals 5.7 mils an hour for our rate. Calculating a lidocaine dilute CRI in mics per kg per minute in a 1 liter fluid bag. Let's see here. So 60 mics per kg per minute is our order. 15 kgs is the weight of our patient, and our rate is 1 times maintenance at 60 mils per kg per day in 1 liter of norm R. We don't know the time yet. And again, 2% lidocaine is 20 mgs per mil. So we're going to calculate our maintenance rate first. 60 mils per kg per day times 15 kgs equals 900 mils per day. 900 mils per day divided by 24 hours per day equals 37.5 mils an hour, which is our rate. The fluid bag time, 1 liter equals 1,000 mils divided by 37.5 mils an hour gives us 26.67 hours as our time. So now we can plug that into our CRI. 60 mics per kg per minute times 15 kgs equals 900 mics per minute. 900 mics per minute times 60 minutes an hour gives us 45,000 mics an hour. 45,000 mics an hour times 26.67 hours is 1,440,000 mics. 1,440,000 mics divided by 1,000 mics per mig is 1,440 milligrams. 1,440 milligrams divided by 20 mgs per mil equals 72 mils lidocaine. So we're going to calculate our dilution now. 1,000 mils minus 72 mils lidocaine is 928 mils of fluid. We want to pull 72 mils of fluid from the fluid bag first, then add 72 mils of lidocaine and mix well. All right, so calculating a KFOS CRI in millimoles per kg per hour. This is going to be in a Buretrol. The reason why we want it in a Buretrol is because we want to reassess our electrolyte panel every 4 to 6 hours. So the CRI dosage range for potassium phosphate is 0.01 to 0.06 millimoles per kg per hour. Our order is to start at 0.01 millimoles per kg per hour for a 15 kg animal. And the rate is at 1 times maintenance, 60 mils per kg per day. The fluids are normal saline and a Buretrol. They don't have to be, they can be LRS or Normar, PLA. The dosage, we don't know yet. And time, 4 hours. The concentration of the phosphorus component is 3 millimoles per mil. The concentration of the potassium component is 4.4 MEQs per mil. In my book, I do discuss going ahead and calculating for the potassium component. We're only going to discuss the phosphorus component. Some veterinarians prefer to calculate for the potassium component, since we are basically more concerned about the potassium versus the phosphorus in causing any kind of detriment to the animal. So they want to go ahead and do the math for the potassium component instead. But this is for the phosphorus component. We first need to find our fluid rate and volume calculation at 1 times maintenance. So 60 mils per kg per day times 15 kgs equals 900 mils per day. 900 mils per day divided by 24 hours per day equals 37.5 mils an hour equals the rate. 37.5 mils an hour times 4 hours equals 150 mils in our Buretrol. So that works out perfectly. The KFOS CRI calculation, 0.01 millimoles per kg per hour. Don't get thrown off by millimoles or MEQs or anything like that. It's just like milligrams and mics. Times 15 kilograms equals 0.15 millimoles per hour. 0.15 millimoles per hour times 4 hours equals 0.6 millimoles. 0.6 millimoles divided by 3 millimoles per mil equals 0.2 mils KFOS. So 0.2 mils KFOS is practically a negligible amount, which is fine to add to a 150 mil Buretrol. KFOS is also always an IVF additive. Do not bolus it, just like you would not bolus KCl. All right, so calculating donor and recipient blood volumes for transfusion. We want to go ahead and state our givens first, or our knowns. So our donor weight is 27.7 kilograms. Our recipient weight is 30.3 kilograms. The desired PCV is 20%. The current PCV is 16% in the recipient patient. The donor PCV from the donor or a pigtail from a bag is 36%. Blood volume for a dog is 90 mils per kg. That's what our shock boluses are based off of, total blood volume. And for a cat, 60 mils per kg. So with or without post-donation IV fluids, so with is 20%, without is 15%, and that's equivalent to the total blood volume that can be safely removed from the donor. So if you do give the post-donation IV fluids, you can take 20% of that total blood volume. And if you do not give post-donation fluids, you can only take 15%. So first you want to calculate the total blood volume from the donor, 90 mils per kg in this case, these are dogs, obviously, times 27.7 kgs equals 2,493 mils total blood volume. So how much can the donor safely give? 2,493 mils times 15% without post-donation fluids equals 373.95 mils. And then the equation for transfusion volume, you want to take desired PCV and subtract it from the current PCV. Divide the donor PCV times the blood volume in mils per kg times the weight of the recipient in kgs. So the calculation with all of these numbers plugged in, our desired PCV is 20%, minus our current PCV of 16% divided by our donor PCV of 36% times blood volume in mils per kg, which is 90 mils per kg, times the weight of the recipient in kgs times 30.3 kgs. So we want to start off by starting from left to right, basically. So we want to subtract the 20% minus 16%, which gives us 4%, and continue on, basically. We want to turn that 4% into a decimal. So 4% is 0.04, and the 36% is 0.36. So we want to now divide 0.04 by 0.36. That gives us 0.111 times 90 mils per kg, times 30.3 kgs. And we want to go ahead and multiply the 90 mils per kg by the 30.3 kgs, and 0.11 times 27 mils total blood volume gives us 302.697 mils, or 303 mils total volume needed by the recipient for a 4% increase in PCV. We're typically aiming for at least a 4% increase. So that number is going to be variable. All right, so calculating drip rates down to drops per second. So let's see here. This is for like, packed red blood cells, fresh whole blood, FFP, and I'm not quite sure of too many other things that are done by gravity drip these days. This is for a calculation over 4 hours for 250 mils. The drip set is 10 drops per mil. We don't know the rate yet. So drops per minute equals total volume in mils over time in hours times the drop factor in GTT, or drops per mil, divided by 60 minutes an hour. So we want to go ahead and plug in the givens into this equation. So 250 mils over 4 hours times 10 drops per mil divided by 60 minutes an hour. And then we want to go ahead and cancel out what has 2 of everything, basically, and keep what doesn't. So we're left with drops per minute. So 2,500 drops over 240 minutes. You want to go ahead and divide after multiplying across, and you get 10.4 drops per minute. Now, 10.4 drops per minute divided by 60 seconds per minute gives you 0.173 drops per second. So 0.173 drops per second times 6 seconds for, this is going to lead into a blood transfusion, by the way, is 1.04 drops per 6 seconds. Now, we want to always round to the nearest whole drop. So that is 1 drop per 6 seconds. And that's going to be this patient's full rate for his blood transfusion. So this is the blood transfusion rates for a gravity drip. So the full rate we just got, which was 1 drop per 6 seconds. And then we want to go ahead and try to half that by with our half rates. So it's actually double, basically, which is slower. So 1 drop per 12 seconds as the half rate is a slower rate than 1 drop over 6 seconds. So that goes ahead and allows us to go ahead and figure out what a quarter of the rate is. So 12 seconds times 0.25 gives us 3 seconds. The 0.25 is 1/4. So 1 drop over 12 seconds plus 3 seconds is 1 drop per 15 seconds. So the half rate is the 1 drop per 12 seconds. So the 3 seconds is basically the number that we are utilizing to go ahead and continuously move up and down in between the quarters. Oops, I'm sorry. Let's see here. Let's go back. And then we have the 3/4 rate, which can finally be figured out. So 12 seconds times 0.25 for 1/4 equals 3 seconds times 3 for 3/4 equals 9 seconds. So you can see that each one of the rates in quarters goes up by 3 seconds. All right. So this is how to calculate blood transfusion rates on a plum pump in mils per hour, basically. You want to go ahead and calculate the total volume in mils to infuse divided by the total number of hours in the transfusion. So calculate the rate to start slowly and titrate, increase the rate gradually every 15 minutes for the first hour of 4 hours of the transfusion. Take the initial mils per hour and which is your total volume divided by time, which is the 4 hours of the transfusion, and divide by 4 to determine the first transfusion rate. Divide by 4 because there's 4 15-minute increments in 1 hour as well. At the 15-minute mark, if the patient's vitals are stable and no obvious signs of reaction are seen, then the rate can be doubled for the next 15 minutes. Continue to double the rate every 15 minutes for the remainder of the first hour and program the rate in your pump accordingly every 15 minutes. So say we have a 250 ml bag of blood over 4 hours to a 27.7 kg canine. 250 mils divided by 4 hours gives us 62.5 mils an hour. So 62.5 mils an hour divided by 4 for those 15-minute increments is going to give us 15.625 mils an hour for the first 15-minute increment. And then 15.625 mils an hour doubled gives us 31.25 mils an hour for the next 15 minutes. 31.25 mils an hour doubled again is 62.5 mils an hour for the next 15 minutes. And then 62.5 mils an hour doubled again is 125 mils an hour for the next 15 minutes. At the 1 hour mark, recalculate the infusion rate to administer the remaining volume by calculating the actual total volume infused by dividing the mils per hour for each 15-minute increment in the first hour by 4 and adding each increment together, or check your pump for the total volume infused, which is easier. You should be using the rate and the VTBI method so that it's alerting you each time that the volume is infused. So 15.625 mils an hour divided by 4 equals 3.9 mils total volume infused. 31.25 mils an hour divided by 4 is 7.8 mils volume infused. 62.5 mils an hour divided by 4 is 15.6 mils volume infused. 125 mils an hour divided by 4 is 31.25 mils infused. So adding all of those up together, we get 58.5 mils as the volume infused. So then you take the mils that you calculated for the TVI and subtract from your starting volume. We get 191.5 mils remaining. Then divide the volume by the remaining hours left to administer the transfusion. So 191.5 mils divided by 3 hours equals 63.8 mils an hour, which is going to be the rate for the next 3 hours. Then program your pump for 63.8 hours with a VTBI of 191.5 mils, and it will be set for the next 3 hours of the transfusion. The TVI for the following 3 hours will be 63.8 mils per hour multiplied by 3 hours, which equals 191.4 mils. To calculate mils per kg per hour, take your mils per hour and divide by the patient's weight. So for example, 15.625 mils an hour divided by 27.7 kgs gives us 0.56 mils per kg per hour. This value is right between the 0.5 and 1 mil per kg per hour, which is the suggested starting point for transfusions. All right, so how to calculate a VenomVet anti-venom infusion over 1 hour in a dog. So there's 2 methods of administration of 1 vial over 30 minutes and 2 hours. One is to utilize a 100 ml bag of crystalloid fluid. Use a 12 mil syringe and an 18 gauge needle to remove 10 mils from 100 mils bag of crystalloid fluid. Use a second 12 mil syringe and 18 gauge needle to withdraw 10 mils of Venom Vet into a syringe and add 10 mils of Venom Vet to 90 mils, the remainder of the bag, for 100 mils total. Slowly flush the length of the line with 0.9% saline when finished with the infusion, so that you're making sure that you are getting, you were giving the full amount to the patient. Or you can use a 1 liter bag of crystalloid at really any size because you're going to use a Burachol. This is my favorite method, basically. If 100 mil bags are not available, use a Burachol with a liter, 500 mils, 250 mils of fluid, and fill a Burachol to 90 mils and add 10 mils of Venom Vet into it. Slowly flush the length of the line with saline when finished with the infusion. Consult a doctor immediately for signs of hypersensitivity reactions or anaphylaxis, or if there's a progression of symptoms. Infusion may be slowed or stopped. Emergency drugs may be utilized, or a second vial may be instituted. I know some DVMs that will use 20 vials. So it's really very variable and patient dependent. For 1 vial over 1 hour, we are going to take the 10 mils of Venom Vet into 90 mils of crystalloid fluid for 100 mils total. It's just like a blood transfusion, basically. It's basically in 10-minute increments for 60 minutes that you're going to be doing vitals checks every 5 minutes until the 20-minute mark to ensure that there's no reaction. So we're going to start low and slow at 0.0625 mils per kg per minute times 20 kgs, which is equivalent to 1.25 mils per minute. 1.25 mils per minute times 10 minutes equals 12.5 mils over 10 minutes, and that is 70 mils an hour. So basically, we just have a nice chart here to make it really easy to see what it is that we need to go ahead and infuse for our VTBIs, as well as where we need to go ahead and have our rates to steadily ramp up. So you can see that it goes from 75 mils an hour to 90 mils an hour to 120 mils an hour. So let's see, the mils per kg per minute may change per patient. Thus the rate in VTBI will change as well. Start at a low rate. 0.0625 to 0.25 mils per kg per minute is a good jumping off point. It doesn't have to be those numbers, but you want about 10 mils or 10 to 15 mils basically for your starting volume infused. Increase the rate every 10 minutes to get the remainder in within 1 hour. Check to ensure that you are within the daily fluid guidelines for that patient with your infusion. The way that you do this is you calculate their maintenance rate. So 60 mils per kg per day times 20 kgs equals 1,200 mils per day. 1,200 mils per day divided by 24 hours, divided by 24 hours a day equals 50 mils an hour. So 1,200 mils per day minus 100 mils of Venom Vet dilution is going to be 1,100 mils a day. So adjust the fluid rate post infusion to 1,100 mils per day divided by 24 hours a day, which is 45.8 mils, which lessens it accounts for the Venom Vet that they received, so that the patient doesn't get overloaded. A good thing is that Venom Vet Plus is coming to market very soon, and I will have a new protocol out for it. And it can be bolused, so we don't have to do these large dilutions. It is the doctor's discretion regarding the rate of the infusion over 30 minutes to 2 hours, and have someone always double check your math before beginning the infusion. Okay, so calculating a heart rate on an ECG strip at 25 millimeters per second. I recommend that you guys go ahead and spend some time with these, and you can download them when the webinar is uploaded to the website. I will have the entire lecture uploaded as well with the links and videos, things like that. So you'll be able to go ahead and access this link and save it and whatnot, so that you can go ahead and download this. But there's several different methods for calculating a heart rate on an ECG. And they're based upon the small boxes and the large boxes. And basically, the easiest method is probably the 6-second method here, which is just counting the number of R waves, which are the top of the QRS complexes, between 6 seconds. So 6 seconds on the strip, basically, which is equivalent to 30 large boxes, then multiply by 10. So you have 7 R waves times 10, 70 is your BPM, beats per minute. So why 10? Because 60 seconds divided by 6 seconds equals 10. You can take a look at all of the different methods and whatnot. They're all pretty similar and close. So calculating a heart rate on an ECG strip at 50 millimeters per second. Again, spend some time with these and download them when you can. There's the small box method, the large box method, which is one R to R interval, and then the 3-second Bic pen method. And I recommend using an actual Bic pen if you're going to do that method, so that you have the measurements proper. Again, this is based on the small boxes and large boxes mostly, and this indicates, what one R to R interval is, and how many, small boxes are there, how many large boxes are there, and basically what 50 millimeters per second is equivalent to, which is 1 second. 30 large boxes is equivalent to 3 seconds or 150 millimeters. So yeah, I definitely want you guys to try to, figure this out, because that's a great skill to have. This is also a really good skill to have, is being able to calculate the PSI that's left in your oxygen tanks if you don't have a system that goes ahead and creates oxygen for you in the hospital and you're still running on tanks. Because if you need to do an emergency surgery, you need to make sure that you've got enough oxygen to last through that. Okay, we're going to be talking about oxygen tanks and the time remaining in them. We need to know a few things going into it. Our cylinder size, the most commonly used in veterinary medicine are H cylinders. The cylinder factor, or the constant, H cylinders are usually 3.14 liters, and the cylinder pressure, so the remaining PSI in the tank, as well as the gas flow, or oxygen flow rate delivered to the patient. We're going to be talking about flow rates first. According to AHA, anything less than 3 to 5 kgs goes on a non-rebreather. Anything greater than 3 to 5 kgs goes on a rebreather. So non-rebreathers are running oxygen flow rates at about 200 to 400 mils per kg per minute. Rebreathers are running at 20 to 40 mils per kg per minute, with no less than 0.5 liters per minute in any patient on a non-rebreather or a rebreather. So for a 20 kg patient, that's greater than 3 to 5 kgs. So they're going to go on a rebreather at 20 to 40 mils per kg per minute. And 20 mils per kg per minute times 20 kgs gives us 400 mils per minute, which is great, but we need it into liters per minute so that we can go ahead and appropriately adjust our dials. So 400 mils per minute divided by 1,000 mils per liter equals 0.4 liters per minute, which is too low, because we just said that no less than 0.5 liters per minute in any patient. So we'll be starting at 0.5 liters per minute. 40 mils per kg per minute times 20 kgs equals 800 mils per minute. So 800 mils per minute divided by 1,000 mils per liter gives us 0.8 liters per minute for our upper ends. So our O2 flow rates for this patient is 0.5 liters per minute to 0.8 liters per minute. Okay, so to go ahead and calculate the time remaining in an oxygen tank that has 200 PSI left on the dial, you're going to go ahead and calculate You've got your O2 flow rate of 0.8 liters per minute for this patient under anesthesia, and your H cylinder constant is 3.14 liters. So we go ahead and calculate 200 times 3.14 liters, and liters cancels out. We divide over 0.8 liters per minute, which gives us 628 over 0.8 minutes. And that gives us 785 minutes total. So 785 minutes divided by 60 minutes an hour gives us 13.083 hours. To go ahead and find out how many minutes that is, 0.083 hours times 60 minutes an hour equals 4.98 minutes or 5 minutes. So the time remaining in our H cylinder is 13 hours and 5 minutes at a flow rate of 0.8 liters per minute. So that is plenty of time to go ahead and get surgery done for this patient with just 200 PSI left. Okay, we're going to be talking about oxygen.
Sorry, let's see here. Okay. All right, so this is that problem basically. All right, so we want to solve for the unknown variables first. So 41 kg patient, the oxygen gas flow rates, we would be on a rebreather at 20 to 40 liters per kg per minute. 20 liters per kg per minute times 41 kgs equals 820 mils per minute. 820 mils per minute divided by 1,000 mils per liter equals 0.82 liters per minute. 40 liters per kg per minute times 41 kgs equals 1640 mils per minute. 1640 mils per minute divided by 1,000 mils per liter gives us 1.64 liters per minute. So the patient's actually running though at 1.2 liters per minute. So you have 75 PSI left with an O2 flow rate of 1.2 liters per minute. And the H cylinder constant again is 3.14. Liters. 75 times 3.14 liters over 1.2 liters per minute. Liters cancels out. It gives us 235.5 over 1.2 minutes, which equals 196.25 minutes. 196.25 minutes divided by 60 minutes an hour gives us 3.26 hours. I'm sorry, 3.27 hours. 0.27 hours times 60 minutes an hour gives us 16.2 minutes. So time remaining is 3 hours and 16 minutes. Good to know is what an E cylinder constant is, which is 0.28 or rounded up to 0.3. So calculating surgical fluid rates in dogs and cats. The cat surgical IV fluid rate is typically 3 mils per kg per hour for animals without cardiac or renal impairment. Consult with a cardiologist or IMED DBM regarding appropriate surgical fluid rate for patients with cardiac or renal impairment. It can go up to 5 mils per kg per hour, but I typically stick with 3. Dog surgical fluid rate is 5 to 10 mils per kg per hour. These rates are very dependent upon their level of dehydration or level of hypovolemia before surgery, and if that's been addressed adequately. So 5 to 10 mils per kg per hour for animals without cardiac or renal impairment. Again, consult with a cardiologist or IMED DVM regarding appropriate surgical fluid rate for patients with cardiac or renal impairment. So our order is 3 mils per kg per hour for a 4.2 kilogram cat without cardiac or renal impairment. So 3 mils per kg per hour times 4.2 kgs. That is going to give us 12.6 mils an hour crystalloid IV fluids for surgery. All right, so calculating an FLK for a 1 liter fluid bag and changing the rate. So we are going to go ahead and take a look at this. The standard order for a FLK is 1 mil per kg per hour, and that's prior to surgery. The intra-op order, it's going to be increased to 2 mils per kg per hour, and then it can be increased from there as well. The patient's weight is 15 kilograms. Fluid is 1 liter bag of whatever flavor you'd like to use. They're all compatible with anything. So calculate your rate and fluid bag time first. So 2 mils per kg per hour times 15 kgs equals 30 mils an hour as your rate. 1,000 mils divided by 30 mils an hour equals 33.3 hours for your fluid bag time. So first we need to figure out I like doing the drugs with loading dose and then CRI all in the same one fall swoop basically, and then move on to another drug rather than calculating loading doses and then CRIs. So for fentanyl, 50 mics per mil is our concentration. Our loading dose range is 0.5 mics per kg to 3 mics per kg. It's there in mgs per kg as well as an IV bolus. Our CRI dosage range is 0.5 mics per kg per hour to 3 mics per kg per hour for a fentanyl CRI and fentanyl, lidocaine, ketamine CRI. The actual loading dosage that we'll be using today is 2 mics per kg. And the CRI dosage is going to be 2 mics per kg per hour. So 2 mics per kg times 15 kgs equals 30 mics. 30 mics divided by 50 mics per mil is 0.6 mil IV fentanyl bolus, and that's equivalent to 1 hour of fentanyl. The CRI, 2 mics per kg per hour times 15 kgs equals 30 mics an hour. 30 mics an hour times 33.3 hours is 999 mics. 999 mics divided by 50 is 19.98 mils or 20 mils of fentanyl. For lidocaine, it is 2% lidocaine, so it's 20 mg per mil concentration. The loading dose range is 2,000 mics per kg or 2 mgs per kg IV bolus. The CRI dosage range is 16.67 mics per kg per minute to 33.3 mics per kg per minute for an FLK, or 1 mg per kg per hour to 2 mgs per kg per hour. The loading dosage is going to be 2 mgs per kg for this patient. The CRI dosage is going to be 1 mg per kg per hour. So 2 mgs per kg times 15 kgs equals 30 milligrams. 30 milligrams divided by 20 mgs per mil equals 1.5 mil IV lidocaine bolus. And then CRI, 1 mg per kg per hour times 15 kgs, 15 milligrams an hour. 15 milligrams an hour times 33.3 hours equals 499.5 milligrams. 499.5 milligrams divided by 20 mgs per mil equals 24.975 mils or 25 mils of lidocaine. Ketamine is 100 milligrams per mil for the concentration. Loading dose range is 500 mics per kg to 2,000 mics per kg, or 0.5 mgs per kg to 2 mgs per kg IV bolus. CRI dosage range is 2 mics per kg per minute to 10 mics per kg per minute, or 0.12 mgs per kg per hour to 0.6 mgs per kg per hour. We'll be utilizing 0.5 mgs per kg for the loading dosage and 0.15 mgs per kg per hour for the CRI dosage. The loading dose is 0.5 mgs per kg times 15 kgs equals 7.5 milligrams. 7.5 milligrams divided by 100 mgs per mil equals 0.075 mils IV ketamine bolus. The CRI is 0.15 mgs per kg per hour times 15 kgs equals 2.25 milligrams an hour. 2.25 milligrams an hour times 33.3 hours equals 74.925 milligrams. 74.925 milligrams divided by 100 mgs per mil equals 0.749 milligrams or 0.75 mils ketamine. So fentanyl is 20 mils, lidocaine is 25 mils, ketamine is 0.75 mils. You want to add all of those up, you get 45.75 mils. And you want to go ahead and remove 45.75 mils first from the 1,000 milliliter bag first, and replace with all 3 drugs, which is equivalent to the 45.75 mils. Nope. To change the rate of the FLK, increase or decrease the FLK rate by 0.5 to 1 mil per kg per hour at a time, depending on the patient's pain response under anesthesia and DVM preference. All right, so vasopressor CRIs. This is going to be for dopamine, 40 mg per mil dilute. Okay. This is also light sensitive, which we indicate. Our order is 5 mics per kg per minute. Our weight is 15 kgs. Our rate is going to be 5 mils an hour. Our fluid is 60 mils of saline, and time is unknown at this point. Concentration is 40 mgs per mil. We calculate our fluid time first, so our fluid bag time, and so 60 mils divided by 5 mils an hour gives us 12 hours. So calculating our CRI next, 5 mics per kg per minute times 15 kgs equals 75 mics per minute. 75 mics per minute times 60 minutes an hour equals 4,500 mics an hour. 4,500 mics an hour times 12 hours equals 54,000 micrograms. 54,000 mics divided by 1,000 mics per mg equals 54 milligrams. 54 milligrams divided by 40 mgs per mil equals 1.35 mils dopamine. So to calculate our dilution, 60 mils minus 1.35 mils dopamine, that would leave us with 58.65 mils diluent. All right, so dobutamine, 12.5 mg per mil dilute. Let's see, our order is 10 mics per kg per minute. Our weight is 31 kgs. Our rate is, it's going to be run at 10 mils an hour. Fluid is 60 mils. And time unknown, but very easy to figure out. And 12.5 mg per mil is our concentration. So our fluid time is 60 mils divided by 10 mils per hour equals 6 hours. Calculate your CRI next. 10 mics per kg per minute times 31 kgs equals 310 mics per minute. 310 mics per minute times 60 minutes an hour equals 18,600 mics per hour. I'm sorry, mics per hour. And then 18,600 mics per hour divided by 1,000 mics per mg equals 18.6 mgs an hour. 18.6 milligrams an hour times 6 hours equals 111.6 milligrams. 111.6 milligrams divided by 12.5 mgs per mil equals 8.9 mils dobutamine. So calculate your dilution. 60 mils minus 8.9 mils dobutamine means that you're going to have a 51.1 mil amount of diluent. Norepinephrine, 1 mg per mil, dilute and titrated. All right. So for treatment of persistent hypotension after adequate fluid volume replacement, this is the dosage for that. 0.05 to 0.1 mic per kg per minute, titrated until a MAP or mean arterial pressure of greater than 65 millimeters mercury is reached, with a max CRI rate of 1 to 2 mics per kg per minute per plums. And the order is 0.05 mics per kg per minute to start and titrate up to 0.1 mics per minute. The weight is 20 kgs. The rate, we're going to run it at 5 mils an hour for 0.05 mics per kg per minute and 10 mils an hour for 0.1 mics per kg per minute. And plan to titrate up to the 10 mil an hour dose as ordered, but stay at the rate that achieves clinical response. Fluids are unknown. Time is 1 hour with dose titrated until clinical response is achieved. Concentration is 1 mg per mil. We're going to be titrating every 30 minutes for 1 hour. So 0.05 mics per kg per minute times 20 kgs equals 1 mic a minute. 1 mic a minute times 30 minutes equals 30 micrograms. 30 micrograms divided by 1,000 mics per mg equals 0.03 milligrams. 0.03 milligrams divided by 1 mg per mil equals 0.03 mils norepi for 30 minutes at 0.05 mics per kg per minute. So for the 0.1 mic per kg per minute, we are going to multiply that by 20 kgs and we get 2 mics a minute. 2 mics a minute times 30 minutes gives us 60 mics. 60 mics divided by 1,000 mics per mil equals 0.06 milligrams. 0.06 milligrams divided by 1 mg per mil equals 0.06 mils norepi for 30 minutes at the 0.1 mic per kg per minute. So 5 mils plus 10 mils is 15 mils total volume because we are taking our rates basically and going ahead and making that our total volume. So 0.03 mils plus 0.06 mils equals 0.09 mils of norepi. 15 mils minus 0.09 mils norepi equals 14.91 mils of diluent. So let's see here. Our diluted rate is 5 mils an hour for the first 30 minutes and then 10 mils an hour for 30 minutes to the 60-minute mark. And then if the 5 mils an hour works and gets the mean arterial pressure above 65, then it can stay there. It doesn't need to be titrated up. So the norepi volumes and the rate are listed here as well. Okay, so for dopamine stock solution calculation, dopamine 40 mg per mil. It's a positive inotrope. It is a vasopressor and there's no loading dose. The CRI dosing range for canines and felines is 0.12 to 1.2 mg per kg per hour or 2 to 20 mics per kg per minute. You're going to basically just dilute 0.3 mils of 40 mg per mil dopamine into a 60 mil syringe of normal saline, giving a dilution of 0.2 mg per mil or 200 mics per mil. The way that you basically get a rate is by doing the rate change in mils per kg per hour. So you're going to start at 0.6 mils per kg per hour, which is equivalent to 2 mics per kg per minute. The way that we avoid mathing very much with these stock solutions is that we're not calculating for that 2 mics per kg per minute. We're calculating for that 0.6 mils per kg per hour because all we have to do is multiply by the weight and we have our rate. So you're going to run 1 to 2 mils per kg per hour, run at 1.2 to 1 to 2 mils per kg per hour for moderate hypotension. But for severe hypotension, you're going to run it at 3 to 4 mils per kg per hour and increase up to 6 mils per kg per hour if necessary. So our order is 0.6 mils per kg per hour, weight is 10 kgs, and we just need to find our rate. So 0.6 mils per kg per hour times 10 kgs equals 6 mils an hour. And that 0.6 mils per kg per hour is equal to 0.12 mgs per kg per hour or 2 mics per kg per minute. How to convert between mgs per kg per hour and to mics per kg per minute and vice versa. So 0.12 mgs per kg per hour divided by 60 minutes an hour gives us 0.002 mgs per kg per minute. 0.002 mgs per kg per minute divided by, multiplied by 1,000 mics per mg equals 2 mics per kg per minute. 2 mics per kg per minute times 60 minutes. This is basically the inverse of that process. Equals 120 mics per kg per hour. 120 mics per kg per hour divided by 1,000 mics per mg equals 0.12 mgs per kg per hour. Dopamine is preferred for cats over dobutamine because studies are unsure if cats have the receptors for dobutamine despite the availability of dosing information for cats. And again, because this extends beyond the 60 mils just by 0.3, you may not be able to use body weight mode on your syringe pump. Norepinephrine stock solution calculation. Let's see. So norepi, 1 mg per mil is a vasopressor, must be diluted in D5W. It oxidizes in normal saline. You have to titrate it to effect. So there's no loading dose. The CRI dosing range canine and feline is 0.006 to 0.12 mg per kg per hour, which is equivalent to 0.1 to 2 mics per kg per minute, with 0.4 mics per kg per minute as the median effective dose. The onset of action is 1 to 2 minutes. Your titration, you're going to titrate the dosage up in increments of 3 minutes until the desired effect is achieved with serial blood pressures every 3 minutes. Continually monitor the blood pressure. The goal mean arterial pressure is greater than 65 millimeters mercury again. For renal impaired patients, it's greater than 75 millimeters mercury though. And you're going to have continuous ECG going, and UOP monitoring is required. So you're going to dilute 1.45 mils of norepi into 60 mils of D5W, giving a dilution of 24 mics per mil. You're going to start the CRI at 0.5 mils per kg per hour and increase up to 5 mils per kg per hour. So our order is 0.5 mils per kg per hour for a 10 kg animal, and we just need to find our rate. So 0.5 mils per kg per hour times 10 kgs equals 5 mils an hour. 5 mils an hour equals 0.006 mgs per kg an hour, or 0.1 mics per kg per minute. Again, body weight mode. Esmolol dilute titrated cardiac CRI calculation. So this is where things really start to be advanced, basically. I honestly don't know too many techs that really know this math that well. So this is, a great opportunity to learn it. So esmolol is a potent drug. You have to dilute loading doses, intermittent boluses, the titration, and CRI. It's compatible with D5W, LRS, half-strength saline, and normal saline. You want to dilute at least 1-to-1. Monitoring is continuous ECG, heart rate, and serial BPs. Dosing, this is the dosing range for treating or assisting in treatment of ventricular tachyarrhythmias in dogs and cats. The loading dose is 0.25 to 0.5 mg per kg, or 250 to 500 mics per kg. And you want to give it IV diluted over 2 to 5 minutes. Intermittent boluses are 0.05 to 0.1 mgs per kg, or 50 to 100 mics per kg. Give slow IV diluted every 5 minutes up to a maximum dose of 0.5 mgs per kg, or 500 mics per kg. The CRI dosing range is 10 to 200 mics per kg per minute diluted, titrated up to the target dose. The order that we're going to be working with is the loading dose of 375 mics per kg IV, dilute 1-to-1, slow push over 5 minutes. The CRI is 50 to 100 mics per kg per minute, diluted 1-to-1, target dose 100 mics per kg per minute, and titrated up to the target dose every 10 minutes. The weight is 3.6 kgs. We don't know the rate. We don't know the fluids. The time is going to be over 1 hour with the CRI titrated up every 10 minutes. I'll show you that math. And the concentration is 10 mgs per mil, or 10,000 mics per mil. So the loading dose is 375 mics per kg, slow push IV over 5 minutes, dilute 1-to-1. So 375 mics per kg times 3.6 kgs equals 1350 micrograms. 1350 micrograms divided by 1,000 mics per mg equals 1.35 milligrams. 1.35 milligrams divided by 10 mgs per mil equals 0.135 mils esmolol, or 0.14 mils esmolol. Dilute at least 1-to-1, so 0.14 mils esmolol to plus 0.14 mils diluent equals 0.28 mils total volume. So give 0.28 mils over 5 minutes via IV slow push. How much do you give a minute? So 0.28 mils divided by 5 minutes is 0.056 mils per minute. So administer 0.06 mils per minute on your syringe via IV slow push over that 5-minute period. To calculate the intervals for the CRI is going to be between 50 and 100 mics per kg per minute, and we're including all of these dosing ranges in the same syringe. So the intervals are 50, 60, 70, 80, 90, and 100 mics per kg per minute. So that's 6 intervals that are separated by 10 mics per kg per minute. So 60 minutes divided by 6 intervals equals 10 minutes per interval of 10 mics per kg per minute over 60 minutes, which is 1 hour. So for the you first need to figure out your titration dose, which is 10 mics per kg per minute. So you take 10 mics per kg per minute times 3.6 kgs, and that is 36 mics a minute. 36 mics a minute times 10 minutes equals 360 mics. 360 mics divided by 1,000 mics per mg equals 0.36 milligrams. 0.36 milligrams divided by 10 mgs per mil equals 0.036 mils esmolol, or 0.04 mils esmolol. You want to dilute it again at least 1 to 1. So 0.04 mils esmolol plus 0.04 mils of diluent gives you 0.08 mils of total volume. To figure out your rate, it's going to be 0.08 mils total volume divided by 10 minutes, which gives you 0.008 mils per minute. 0.008 mils per minute times 60 minutes an hour equals 0.48 mils an hour. Now we can figure out our starting dose, basically. And there's 2 ways to go ahead and figure this out, and I'm going to show both of them to you, but this is the first way. So 50 mics per kg per minute times 3.6 kilograms equals 180 mics per minute. 180 mics per minute times 10 minutes equals 1,800 mics. 1,800 mics divided by 1,000 mics per mg equals 1.8 milligrams. 1.8 milligrams divided by 10 mgs per mil gives you 0.18 mils esmolol. 1-to-1 dilution, 0.18 mils esmolol plus 0.18 mils diluent gives you 0.36 mils total volume. Well, that wasn't supposed to be there. Okay. So this is option 2. So you're going to perform the calculations for each 10 mic per kg per minute interval, basically. And it's basically, creating, a organized way of getting your volumes basically all laid out. So for 50 mics per kg per minute, we just calculated that. We got 0.36 mils total volume, and then we're going to subtract 0.18 mils of esmolol to ensure that 0.18 mils is our diluent. So we basically go ahead and calculate for each one of the 60, 70, 80, 90, 100 mics per kg per minute and enter all that information in, because then we need to add together all of our volumes of esmolol from all of the 10 mic per kg per minute intervals. We get a total of 1.68 mils esmolol. We want to add together the total volumes for each interval. So that's 3.36 mils total volume. And for a math check, you want to subtract the esmolol volume from the total volume to check the diluent volume is equivalent. So 3.36 mils total volume minus 1.68 mils esmolol gives you 1.68 mils diluent. So that's correct. So the rate and VTBI of a titrated CRI, you want to set the syringe pump with the VTBI programmed so the pump stops and sounds when each VTBI has been delivered, and then input the new rate. So for 50 mics per kg per minute, to figure out the rate, you take the 0.36 mils divided by 10 minutes equals 0.036 mils per minute. 0.036 mils per minute times 60 minutes an hour equals 2.16 mils an hour. And we know that our VTBI, our total volume is 0.36 mils. So that's what's going to get programmed into the pump, and then the rate we just figured out. So you want to do this for each of the 10 mic per kg per minute intervals, and make sure that you have all of that information. There is an easier way to do this, I promise, and I'm going to show it to you in a moment. But I do need to go over the fact that this is a potent drug. Again, we are titrating it to effect. Once the desired resulting ECG rate and rhythm are attained, alert your DVM right away. Pay continual attention to the ECG for heart rate and refractory arrhythmias. And begin to titrate back down at the doctor's discretion when the ECG, heart rate, and BP are stable for a suitable period of time to the doctor. If hypotension or bradycardia are noted, alert the doctor right away, stop the infusion, and reassess the patient. Okay. So this is option 2. This is a much easier way because the other way you have to math out every single one of those. This is a way that shows you how to figure out the rate of change, basically, that you use to put into a table and go ahead and calculate the CRI much easier than mathing out all of those individual CRIs. So for the loading dose, again, 375 mics per kg, slow push, IV over 5 minutes, dilute 1:1. We get 0.14 mils of esmolol, diluted 1:1 with 0.14 mils of diluent, gives us 0.28 mils total volume. Give the 0.28 mils over 5 minutes via IV slow push, and that's 0.06 mils per minute. To calculate the intervals, again, it's the same thing. So you have 6 intervals of 10 mics per kg per minute. 60 minutes divided by 6 intervals is 10 minutes per interval of 10 mics per kg per minute over 60 minutes or 1 hour. So you're going to start at the 50 mic per kg per minute starting dose, and then titrate upwards 10 mics per kg per minute every 10 minutes to the target dose at 100 mics per kg per minute for 1 hour total to the target dose. And you're going to dilute it. You're going to dilute everything at least 1:1. This will be 1:1. Starting the starting dose, you want to go ahead and figure that out first. So 50 mics per kg per minute times 3.6 kgs, 180 mics a minute, 180 mics a minute times 10 minutes, 1800 mics. 1800 mics divided by 1000 mics per mg equals 1.8 mgs. 1.8 mgs divided by 10 mgs per mil equals 0.18 mils esmolol. So 0.18 mils esmolol plus 0.18 mils diluent equals 0.36 mils total volume, which is your VTBI. So the rate, again, you just need to figure this out one time, all of this, 0.36 mils divided by 10 minutes, the 0.036 mils per minute, 0.036 mils per minute times 60 minutes an hour gives us the 2.16 mils an hour. Let's see here. Now we're going to figure out the titration dosage of the 10 mics per kg per minute. Times 3.6 kgs, 36 mics a minute, 36 mics a minute times 10 minutes equals 360 mics. 360 mics divided by 1000 mics per mg equals 0.36 milligrams. 0.36 milligrams divided by 10 mgs per mil equals 0.036 mils of esmolol. You don't have to round. You can keep that. I'm rounding though. 0.04 mils of esmolol. That is one of your rates of change. You will have 4 of them, and it is going to be your esmolol volume, your total volume, your diluent volume, and your rate. So next, with the dilution of 0.04 mils esmolol plus 0.04 mils of diluent, that gives us 0.08 mils of total volume for our rate of change. And the 0.04 mils of diluent volume is also indicated there as a rate of change. For the rate, 0.08 mils total volume divided by 10 minutes equals 0.008 mils per minute. 0.008 mils per minute times 60 minutes an hour gives us a rate of change of 0.48 mils an hour. All right, this is where this all comes into play. So the rates of change, we list them up top. Esmolol is 0.04 mils. that is the volume. Diluent volume is 0.04 mils. The rate is 0.48 mils, and the total volume is 0.8 mils. So for our titration table, we need to have mics per kg per minute, our total volume / VTBI, our esmolol volume, and our diluent volume. And let's see here, also our rate in mils per hour. I apologize that things are a little bit off with the table. But so we start out with our 50 mics per kg per minute, and input those numbers in first. Oops, I'm sorry. And input those numbers in first. And then we want to go ahead and add for each one of these columns, basically. So for the 0.36 mils, we would add the rate of change of our total volume of 0.08 mils in order to get 0.44 mils in the next row. So you add 0.08 mils again, you get 0.52 mils. 0.08 mils again added is 0.6 mils. 0.68 mils added is 0.76 mils. So that is how this table is set up. Esmolol, you just go ahead and input the 0.18 mils from the 50 mic per kg per minute CRI that we figured out, and then add on your esmolol volume of 0.04 mils to each one of those rows. And same with the diluent volume of 0.04 mils. As for the rate, in mils per hour, 2.16 mils per hour is going to be going to have 0.48 mils an hour added to it to get 2.64 mils an hour, and so on. At the end, you want to do a math check and add up the total volume and VTBI column to make sure that everything equals appropriately. So the 1.68 mils of esmolol that we got matches our CRI from earlier. Same with the diluent. And the total volume that we get over in the bottom right-hand corner of the esmolol and diluent basically is equivalent to what we have in the total volume and volume to be infused column. So that checks out. Okay. So for the next one, procainamide, this is a dilute titrated cardiac CRI as well. 2% lidocaine is the drug of first choice, and procainamide, when ineffective, you want to use procainamide when lidocaine is ineffective and serum potassium and magnesium concentrations are adequate. It's compatible with sterile water, saline, and D5W. Monitoring includes continuous ECG, heart rate, and serial BPs. Adverse effects are vomiting and diarrhea. This is dosing for treating or assisting in treatment of severe clinical ventricular arrhythmias in dogs. The loading dose is 2 to 4 mg per kg, and you want to give it IV slowly over 2 to 5 minutes, maximum of 20 mg per kg. If successful in resolution of clinical signs, you're going to start a CRI. CRI is 20 to 50 mics per kg per minute diluted. Titrate up to the target dose every 15 minutes for 1 hour if clinical signs reappear. All right. So our loading dose is 4 mg per kg, IV slow over 2 to 5 minutes. CRI is 20 to 50 mics per kg per minute for a 10 kilogram animal. We don't know our rate. We don't know our fluids yet. Our time is 1 hour, titrating upward, 10 mics per kg per minute every 15 minutes if needed. And we'll do that math. Concentration of procainamide is 100 mg per mil. So loading dose, 4 mg per kg times 10 kgs, 40 mgs. 40 milligrams divided by 100 milligrams per mil equals 0.4 mils procainamide, IV slow over 2 to 5 minutes. 0.4 mils over 5 minutes equals 0.08 mils per minute. All right, so to calculate the intervals, all right, so this is 20 to 50 mics per kg per minute. So 20, 30, 40, 50. That's 4 intervals of 10 mics per kg per minute, basically in between those numbers. So 60 minutes divided by 4 intervals equals 15 minutes per interval of 10 mics per kg per minute over 60 minutes or 1 hour. All right, so we calculate our CRI starting dose, 20 mics per kg per minute times 10 kgs equals 200 mics per minute. 200 mics per minute times 15 minutes equals 3,000 micrograms. 3,000 micrograms divided by 1,000 micrograms 1,000 micrograms per milligram equals 3 milligrams. 3 milligrams divided by 100 milligrams per mil equals 0.03 mils procainamide. The titration dose is 10 mics per kg per minute. So 10 mics per kg per minute times 10 kgs equals 100 mics per minute. 100 mics per minute times 15 minutes equals 1,500 micrograms. 1,500 micrograms divided by 1,000 mics per mig equals 1.5 milligrams. 1.5 milligrams divided by 100 mgs per mil equals 0.015 mils procainamide. This is one of the rates of change. So the procainamide volume. We are diluting to 10 mics per kg per minute equals 1 mil total volume. This is also one of our rates of change. So 1 mil total volume equals 0.15 mils procainamide. I'm sorry, 1 mil total volume minus 0.015 mils procainamide equals 0.985 mils diluent. And this is also a rate of change. Our actual rate, 1 mil total volume divided by 15 minutes equals 0.067 mils per minute. 0.067 mils per minute times 60 minutes an hour equals 4.02 mils an hour or 4 mils an hour. Again, the rate is a rate of change. So make sure you have those 4 rates of change. Okay, so procainamide volume, diluent volume, our rate, and our total volume are all represented here. Okay. Now I have the 10 mic per kg per minute in here this time to show you the addition basically that you would be doing in each of the columns. So that's what it's representative of. But you can always start these at, the starting point as well and just add from there. So basically what we're doing is, taking the 1 mil total volume in column 1 for 20 mics per kg per minute and adding it just over and over and over again down the line. The procainamide volume, again, 0.015 mils gets added onto 0.03 mils to make 0.045 mils. 0.06 mils, 0.075 mils. If you were to individually math out each one of these CRIs, you would get all of these numbers. So this is just an easier way of going ahead and completing multiple CRIs with just very little math. You get the same things when it comes to the diluent at 0.985 mils volume. 1.97 plus 0.985 gives you 2.955 plus 0.985 again gives you 3.94 and so on. For the mils per hour, it's going up in increments of 4. That's pretty easy to figure out. Again, we want to do our math check of our total volume and our VTBI we get 14 mils on the left-hand side. We go ahead and add up our volume of procainamide, 0.21 mils procainamide plus 13.79 mils of diluent, and that also gives us 14 mils total volume in the right-hand corner. So sodium nitroprusside, titrated cardiac CRI calculation. This is light sensitive and it's a potent drug as well. Uses and indications. It's for the adjunctive treatment of acute heart failure, cardiogenic shock, and pulmonary edema. CRI dosage, there's no loading dose. Cats, 0.5 to 5 mics per kg per minute, titrated up until target dose or predetermined BP is attained, desired / desired effect. Dogs is 1 to 5 mics per kg per minute, titrated up until target dosage or predetermined blood pressure is attained / you reach the desired effect. Blood pressure targets a mean arterial pressure of 70 millimeters mercury or systolic blood pressure of 90 to 100 millimeters mercury. Titration, titrate the dosage up to the desired effect in 0.5 to 1 mic per kg per minute increments every 10 to 15 minutes, as long as the BP remains stable and until perfusion and pulmonary function improves. The maximum CRI rate is 10 mics per kg per minute, but most recommend a much lower max rate at 5 mics per kg per minute. Monitoring is serial BPs, heart rate, acid-base balance, so your venous blood gases, arterial blood gases, electrolytes, especially the sodium, because this obviously has sodium in it. Compatibility, it is incompatible with other solutions. Use D5W only. Okay, so our order is 1 mic per kg per minute. You're going to titrate upwards in 1 mic per kg per minute increments until the target dose of 5 mics per kg per minute or the predetermined blood pressure is attained / you reach the desired effect. It is a 10 kg canine. We don't know the rate or fluids at this time. It's going to be 1 hour with 12-minute increments, and we'll map that out in a second. Concentration is 25 mg per mil for sodium nitroprusside. Let's see here. So the intervals are calculated a little bit differently for this. So we're going to take 5 mics per kg per minute divided by 1 mic per kg per minute. And that gives us 5 intervals of 1 mic per kg per minute. Basically over 1 hour. So 60 minutes divided by 5 is 12 minutes per interval of 1 mic per kg per minute over 60 minutes. So now we can go ahead and calculate our CRI. 1 mic per kg per minute times 10 kgs, 10 mics a minute, 10 mics a minute times 12 minutes, 120 mics, 120 mics divided by 1,000 mics per mg equals 0.12 milligrams. 0.12 milligrams divided by the concentration of 25 mg per mil equals 0.0048 mils nitroprusside. This is a rate of change. And just calculate for 1 mic per kg per minute because the starting dose and the titration intervals are the same. So we're titrating in increments of 1 mic per kg per minute. But our starting dose is also 1 mic per kg per minute. So we don't need to repeat that math. So dilution for 1 mic per kg per minute equals 1 mil total volume. This is also a rate of change. So take note of that. 1 mic per kg per minute equals 1 mil minus the 0.0048 mils of nitroprusside volume. And that gives us 0.9952 mils diluent volume. This is also a rate of change. And let's see here. Our rate, 1 mil total volume divided by 12 minutes gives us 0.083 mils a minute. 0.083 mils a minute times 60 minutes an hour equals 5 mils an hour, which is also a rate of change. And then it talks about setting your syringe pump again. So this is the rates of change. Nitroprusside volume is 0.0048 mils. Diluent volume is 0.9952 mils. The rate is 5 mils an hour. The total volume is 1 mil. And we've got 1 to 5 mics per kg per minute shown here. So basically, we are adding 1 mil down this column, and we get 15 mils total volume, basically. Nitroprusside, we continuously add 0.0048 mils in each of the rows, and we get a total volume of 0.072 mils nitro. Our diluent volume, we add 0.9952 mils down the row, and we end up getting 14.928 mils diluent. And we get the 15 mils again in the lower right-hand corner. And then we just go ahead and keep adding on 5 mils an hour down the row, and very easy to figure out. All right, so diltiazem dilute titrated cardiac CRI calculation. It's compatible with D5W and normal saline. The monitoring includes continuous ECG, heart rate, and serial BPs. Dosing for treating or assisting in treatment of supraventricular arrhythmias in dogs. Loading doses between 0.05 and 0.1 mg per kg. Give IV over 2 minutes. It may be repeated up to 2 times with 5 minutes in between doses, or 0.25 mg per kg over 2 to 5 minutes. Dosage may be carefully increased up to a total dose of 0.5 mg per kg IV over 5 to 10 minutes. The CRI is 2 to 6 mics per kg per minute diluted. Titrate up to a target dose every 20 minutes for 1 hour. CRI when the arrhythmia recurs before PO dosing is feasible. So for the CRI, our order and for the loading dose and CRI are here. So 0.1 mg per kg IV over 2 minutes with a 2 to 6 mic per kg per minute CRI and a 10 kg dog. We don't know the rate of fluids yet. 1 hour titrating upward every 20 minutes, and concentration of diltiazem is 5 mg per mil. So for our loading dose, 0.1 mg per kg, 10 kgs, we get 1 milligram. 1 milligram divided by 5 mg per mil equals 0.2 mils. Diltiazem IV over 2 minutes. 0.1 mils per minute is basically what we're getting there. We don't really need to map that out, do we? Calculate your titration intervals, 2 to 6 mics per kg per minute, just like the nitroprusside. We're going to take 6 mics per kg per minute divided by 2 mics per kg per minute, and we get 3 intervals. 60 minutes divided by 3 equals 20 minutes. So titrate by 2 mics per kg per minute every 20 minutes for 1 hour. And for the CRI, 2 mics per kg per minute times 10 kgs equals 20 mics a minute. 20 mics a minute times 20 minutes equals 400 micrograms. 400 micrograms divided by 1,000 mics per mg equals 0.4 milligrams. 0.4 milligrams divided by 5 mgs per mil equals 0.08 mils diltiazem, and that is a rate of change. The dilution for 2 mics per kg per minute equals 2 mils total volume, which is a rate of change. Would be 2 mics per kg per minute equals 2 mils minus 0.08 mils. Diltiazem volume equals 1.92 mils diluent volume. Again, rate of change. To get the rate, 2 mics per kg per minute equals 2 mils over 20 minutes. 2 mils times 3, which is a unit of time, equals 6 mils an hour, which is our rate, and our VTBI is 2 mils. Again, this is a rate of change. So diltiazem volume, 0.08 mils, diluent volume, 1.92 mils, rate, 6 mils an hour, total volume, 2 mils. Those are the things that are going to change in between each interval. So the titration table for 2 to 6 mics per kg per minute, we're going to add on basically just like we did in all of the others. And just go straight down the line, and everything equals up. All right, so propranolol, this is basically not a titrated cardiac drug, but it is a cardiac drug that requires some calculation and administration instructions. It's compatible with D5W, LRS, and regular and normal saline. The monitoring includes continuous ECG monitoring, heart rate, and serial BPs. You will see dogs that bite into asthma inhalers, basically albuterol, go ahead and receive propranolol a lot of the time. So loading dose is 0.02 mg per kg IV slow over 2 to 3 minutes, no more than 1 milligram a minute. Intermittent bolus dosing includes 0.02 mg per kg IV slow over 2 to 3 minutes, no more than a milligram a minute, titrating the dosage up to effect to a maximum of 0.1 mg per kg. And it can be repeated every 8 hours. The order that we are working with for the loading dose is 0.02 mg per kg IV over 2 to 3 minutes, and an intermittent bolus dose, 0.02 mg per kg titrated up to effect to a maximum of 0.1 mg per kg, give IV slow over 2 to 3 minutes. The weight is 10 milligrams. The concentration is 1 mg per mil. So these are just boluses, basically. There's no CRI with this. So for the loading dose, it's just dose times weight divided by concentration, and we get 0.2 mils per pranolol over 2 to 3 minutes, which is 0.1 mils a minute if given over 2 minutes. For the intermittent bolus dosing, it's 0.04 mg per kg times 10 kgs, which gives us 0.4 milligrams. 0.4 milligrams divided by 1 mg per mil gives us 0.4 mils per pranolol IV over 2 to 3 minutes, which is 0.2 mils per minute if given over 2 minutes. Repeat the 0.04 mg per kg IV dose to reach a maximum of 0.1 mg per kg. This is if needed. And basically, it's just a repeated dose. So that is how that is given. All right, we are at the end here. So we are at our giveaway. So I will kind of be moving some stuff around on the screen so that I can access the Q&A section here in a moment to see, if you guys are able to figure this problem out. So this is a scenario. A technician delivered a K-Max CRI to a 43.4 kilogram patient at a 6.5 mils an hour over a period of 4 to 6 hours, and did not notate her CRI administration, nor did she create a label for the syringe. So the patient had a Y set in place with 1 liter of LRS running at 163 mils an hour. The DVM originally ordered the K-Max CRI to be run at 0.3 MEQs per kg per hour. The concentration of KCl is 2 MEQs per mil. Your task is to backmath the K-Max CRI she created to find out where she went wrong and how. And a tip is to calculate for 4 and 6 hours. So I'll leave that up on the screen for a moment. When you input your answers into the Q&A section, make sure that you have the 4 and 6 hour answers. Okay, I'm going to see if I can go back to the webinar here and see if anyone's going to participate in this. Okay. All right. So it doesn't look like anybody is going to be participating in this. Oops. Let's see. Okay. All right. So essentially, for the answer, we want to first find the approximate total volume utilized over 4 and 6 hours. So 6.5 mils an hour times 4 hours equals 26 mils. 6.5 mils an hour times 6 hours equals 39 mils. Set up your knowns and givens for Kmax. Your order is 0.3 MEQs per kg per hour. Your weight is 43.4 kgs. The rate is 6.5 mils an hour Kmax, 163 mils an hour LRS. Fluids are 26 to 39 mils Kmax. We just figured that out. 1 liter of LRS is running concurrently. The time is between 4 and 6 hours, and concentration is 2 MEQs per mil. Then you want to just solve the CRI for 4 hours and 6 hours. So 0.3 MEQs per kg per hour times 43.4 kgs equals 13.02 MEQs an hour. 13.02 MEQs an hour times 4 hours equals 52.08 MEQs. 52.08 MEQs divided by 2 MEQs per mil equals 26.04 mils KCl. To figure out the rate again, 26.04 mils divided by 4 hours, 6.51 mils an hour. Kmax CRI for 6 hours, 0.3 MEQs per kg per hour times 43.4 kgs equals 13.02 MEQs an hour. 13.02 MEQs an hour times 6 hours equals 78.12 MEQs. 78.12 MEQs divided by 2 MEQs per mil equals 39.06 mils KCl. And the rate is 39.06 mils divided by 6 hours, which gives us, again, 6.51 mils an hour. So how did she mess this up? What is messed up about this CRI? The technician did not perform any dilution math to dilute the CRI. It was given straight as straight KCl. KCl, especially at Kmax dosages, must always be diluted. Delivering straight KCl can cause the patient to go into cardiac arrest or experience arrhythmias that could be fatal. That's why potassium chloride is utilized in the human lethal injection protocol. This patient was lucky enough to have a rate of 163 mils an hour of LRS IV fluids going through the same IV catheter through the Y set, which likely saved this patient's life, though through the dilution it was providing intravascularly, which is not ideal. This is a true event and was presented as a problem to VetMedMath stat math service when leadership could not figure out the back mathing in hospital themselves. A proper dilution ratio for patients without fluid restrictions is at minimum 1:4 for Kmax. For fluid restricted patients, I've seen dilutions as low as 1:1 instituted by criticalists, though. Also, you always want to run lights panels every 4 to 6 hours when supplementing with Kmax or KFOS or KCl to see if the dosage needs to be changed. So I just want to thank you all for attending tonight. If you have any questions or concerns that are not answered in the Q&A, which I think we're running a little late at this point, please feel free to email me directly at Kristin@vetmedmath.com with your questions. The screenshots provided tonight are from my book, The Veterinary Technician's Guide to Emergency and Critical Care. You can receive 50% off of all ebooks for attending this webinar, just $22.50. The link is there. It will be available on the website, the VetMedology and VetMedMath websites later. And the discount code is VetMedology Feb24 in all caps. So thank you for watching. Please do not forget to take the survey that you're redirected to after the webinar. Your feedback is very important to us. VetMedology upcoming live webinars for March, ADHD and neurodivergence in veterinary professionals for leadership and support staff, partnership with leading veterinary teams and VetMedology. April 2024 is going to be the phone triage masterclass with Shadia Rayfedge, DVM and boarded surgeon and founder of Vet Triage. And we have so many more to announce coming next month. So I am very excited to let those be known. So to earn your certificate, again, you want to go to www.vetmedology.com and create an account or subscribe to VetMedology for just $10 a month. navigate to the Your CE portal, and this webinar will be available to you by tomorrow. It'll likely be available tonight to complete the required quiz to earn your free certificate of completion by no later than Saturday, 2/17/24 at midnight. At that time, you will lose access to the course in the Your CE portal if you are not a VetMedology subscriber. VetMedology subscribers receive free access to all live webinars as well. All right. So that is all. Let's see here. Does anyone have any questions or anything like that that they want to put in the Q&A before we sign off for the night? Oh, you're so welcome, Kat. Okay. All right, guys. So I am going to stop sharing my screen here and sign off for the night. Thank you so much for attending. I'm so glad this didn't run into 3 hours. Have a good night.